Hello, my name is Mohammad Ihsan Haikal Sukmana from Hasselplaner Institute, University of Potsdam, Germany. Today, I would like to present my paper, A Brokerage Approach for Secure Multi-Cloud Storage Resource Management for EAI SecureComm 2020. So nowadays, more enterprises and individuals are moving their data to the cloud. So the data that was stored in the paper are then stored in the floppy disk, CD/DVD, or even now pen drive are now stored in the cloud. It provides better data availability, scalability, service reliance, and even less maintenance than hosting your own data center to just store your own data. However, cloud storage service outage could still happen, even though the uptime is guaranteed up to 99.9%. If the outage happens, this could lead to service unavailability, vendor lock-in, or even financial loss to name a few. For example, one of the most famous and used storage service called AWS S3 was down for 4 hours in 2017, and this made hundreds of websites and web services to be down as well, with millions of dollars of financial loss. So therefore, more and more cloud customers are using multi-cloud storage approach, which is the usage storage service for multiple cloud service providers. This provides data availability and service reliability in case of outage happen to maybe one or even several cloud service providers. The multi-cloud storage approach itself utilizes various data storage strategies by storing multiple objects across various cloud service providers, such as erasure coding, replication, or even fragmentation. So now we are talking about cloud storage resource management, which is the process of managing and allocating available resources in the cloud for the requiring entity to fulfill its requirements and objectives. And there's this concept of share responsibility model that is used in the cloud computing, which is cloud customers are responsible to manage available cloud storage resources from one or multiple cloud providers depending on the number of the services subscribed by the cloud customers. There are several reasons or objectives why cloud customers would like to do cloud storage resource management. For example, that they wanted to make sure the data can only be accessed by authorized users, making sure the data is always available 24/7 in any cases, or even to just save money by deleting unimportant data from the cloud. So now there are three entities involved in the cloud resource management process. First one is the cloud service provider itself. As I've mentioned earlier that we have share responsibility model, this also applies to cloud service provider. They are responsible to manage the cloud infrastructures coming from the hardware, firmware, or even the software such as the API and SDKs that are used by cloud customers. They must fulfill service level agreement agreed between the cloud service provider and the cloud customers. So we assume that the cloud service provider will execute commands issued by the cloud customers no matter what. Now we have cloud customer, which could be individual or enterprise that subscribes to one or maybe multiple cloud providers. They manage cloud resources required by the cloud end users. And the cloud end user itself could be users, application, or services that are exist or work under the cloud customer. They require certain access to the cloud resources to be able to do their jobs. Now we are talking about the challenges of the cloud storage resource management. And here we only will name a few. The first one is that like cloud providers actually do not have to follow any cloud computing standards available in the market, which means that each cloud provider could implement their own services and APIs differently to other cloud providers, which means that the cloud customer have to deal with the heterogeneity of the cloud providers. They need to be able to collect and process cloud storage resource information across different cloud providers, and this is so difficult to ensure the constant global cloud resource state across different cloud providers. And obviously as well that the more cloud providers subscribed by the cloud customers, the more complex it's gonna be to be managed by the cloud customers. And the multi-cloud APIs and tools available in the market, such as Apache G Cloud, for example, might not be sufficient to help cloud customer to deal with the heterogeneity of the cloud providers. And as well as that cloud customer need to ensure that the cloud storage resources should be correctly and securely configured by following cloud security best practices, or even to ensure that it follows the requirements of the cloud end users. So therefore, in this presentation, we propose unified multi-cloud storage resource management framework. This will help to securely manage cloud storage resource lifecycle from the customer's perspective for cloud end users. Currently, we are only focusing on the object storage and identity access management, or IAM, services for Amazon Web Services and Google Cloud. It consists of unified cloud storage resource model and unified multi-cloud storage resource management platform. So the first one, what we're going to talk about is the unified cloud storage resource model. It solves the challenges of managing the information from various cloud storage resources and cloud access control models from different cloud providers due to the heterogeneity of the cloud providers. So it continues our previous work of unified cloud access control model, and our previous work mainly focuses on the use case of cloud storage broker service. And our current work model right now can be implemented for different use cases. And obviously as well, this could also be used to store the state of the cloud storage resources and analyze the information of the cloud storage resources for various use cases, such as compliance check with the cloud security best practices, or to discover the relationship between the cloud resources. So here's the graphical representation of our unified cloud storage resource model. So in here, we'll have the bucket, which is like the, the storage for your data or object in the cloud, and the bucket and the object are actually configured uh, using the policy and the access control list, which will decide then who are going to be able to access the bucket or even the object itself. And the policy and the ACL actually consists of the list of privileges or list of actions that will decide whether what kind of action that are allowed or not allowed in the certain state. And then the policy itself actually is applied to the services of the cloud provider itself, or even the account of that the entity of the IAM services in the cloud provider. And each account, in order to be able to access the cloud resources, they require the access key. So think of it as like a username and passwords of that is used by the account to be able to authenticate themselves to the cloud providers. And also each bucket also may have its own login configuration, where any activity is happening on the monitor bucket, this will be delivered to the target bucket. So now we have the second contributions of this presentation, which is the unified multi-cloud storage resource management platform. It provides holistic feasibility and centralized cloud storage resource management capabilities across multiple cloud providers. Our management platform actually provides a cloud abstractions by as we build an abstraction layer on top of the cloud providers API and SDKs that are provided by the cloud provider itself. And here we use this cloud brokerage approach to manage the relationship between cloud customers, cloud storage resources, and multiple cloud provider and cloud end user. As you can see that the platform mediates the relationships between the cloud providers, cloud customer itself, and the cloud end users. So it is able to collect, pre-process, and store cloud storage resource information following our unified cloud storage resource model as we have explained before. So now we are focusing on the different processes. The first one we're focusing on is the resource discovery process, which is able to automatically discover all cloud storage resources in multiple cloud providers. It transforms the information of the cloud resources such as here, to our proposed unified format, which will become something like this. This is an example representation of an AWS bucket, and also that it compares the live state of cloud resources, or as we call it, cloud state in here, compare with the state of the cloud resources persisted in the database in here, such as an expected state. So in here, when the cloud state and expected state are compared, if there is any difference whatsoever, then the engine will raise an alert or raise an information saying that there are, for example, a new bucket created, or a configuration of the bucket is modified for some reasons, and the cloud customer then could decide whether to retain the expected state, meaning by to reverse the changes happening on the cloud state, or maybe to just save whatever happening on the cloud state in here and store it in the database and as an expected state. Second one is the resource orchestration process, that is basically focusing on the allocating cloud storage resources, which means that it is able to create, delete, and modify cloud storage resources. Then the idea of the resource orchestration process itself is that it should be able to fulfill the requirement of cloud end users based on the service level agreement. For example, maybe that a bucket should only be accessed by user A, user B, and user C, and user D shouldn't be able to access this kind of bucket. And in here that we also providing, other than the manual cloud resource orchestration, for example, using the user interface in here, we're also providing an automated cloud resource orchestration using the resource specification template that can be stored in the database and in here, which will make it everything to be automated, and and all of this orchestration then will be translated as by multi-cloud connector as a cloud resource orchestration command. The third process is the resource assessment process. It basically evaluate cloud storage resources against specifications from cloud end users requirements, or maybe the cloud security best practices. It detects if there's any unauthorized modification to the cloud resources. So as I've mentioned before in the resource discovery process, that whatever happening on the cloud state in here will be then compared with the expected state that is persisted in the cloud resource database. And if there is any changes, or maybe there's an unauthorized misconfigurations happening on the cloud resources, we could actually fix it to make sure that the resources are correctly and securely configured. And the last one is actually the resource monitoring process. So the idea was that, like, as we store the data to the cloud, we actually wouldn't know if the data could be authorizedly or unauthorizedly accessed by anyone else. It could be by an unauthorized user, or even maybe by some stranger in the internet. So therefore, what we want to focus on is that how can we do that? How can we monitor the usage and activities of the resource in the cloud providers? So here what we are doing is that we collect the cloud activity logs generated by AWS CloudTrail and Google Cloud Logging. However, still, there are some challenges the cloud customer need to solve to be able to monitor the activities happening in the cloud providers. For example, that each cloud provider has its own logging format structure and information quality. For example, AWS CloudTrail has more information and has a better information quality compared to Google Cloud Logging. And also the thing is that with this logs, cloud activity log files, cloud customer need to be able to actively store, retrieve, and process the cloud activity log files. Otherwise, then the log file might be deleted by cloud provider after a certain period of time. And usually, each cloud provider has its own log processing services, but it's only that it's basically it can process the logs coming in from its own cloud provider, but it wouldn't be work as well as good to process the logs coming in from other cloud providers. So in here, what we're focusing on is to download, store, and pre-process cloud activity log messages from various cloud providers, and of course to resolve the challenges as we have mentioned before. we propose and implement unified cloud activity log format, as you can see here on this table, for example. And on the right, as you see here, that all of these logs coming from AWS CloudThread and Google Cloud Logging will then be parsed in here using this table to have a unified cloud activity log, as well as we store the raw information as well, which will be able to be further processed in the analytics pipeline. By using our unified cloud activity log format, this will help to give overview of the activities happening in the multi-cloud environment and also for further analytics process. So in conclusion, that multi-cloud storage approach becomes a trend in the recent years. However, there are challenges faced by cloud customers to securely and manage cloud storage resources for cloud end users. So therefore, we propose a unified multi-cloud storage resource management framework that allows cloud customers to discover, create, delete, modify, evaluate, and monitor cloud storage resources in various cloud providers. So we are also right now, for the future work, we are currently extending our framework to include other cloud providers and different cloud resource types. For example, from OpenStack or Microsoft Azure, and as well, for example, like virtual machine or even container services. Some of the references that are used for this presentation. Right. Thank you very much for your attention. Any questions, please feel free to message me at muhammad.sukmana@hpi.de. Thank you very much.
I'm presenting our paper named CacheLoc, Leveraging CDN Edge Servers for User Geolocation. My name is Minghui Wei. I'm Assistant Professor in Computer Science Department at Sam Houston State University. This work is in collaboration with Dr. Khalid Rabi'i and Dr. Faisal Kalim in Metropolitan State University. Nowadays, a user's geolocation has become a very essential information for the website. By knowing such information, a website is able to offer a customized service. For example, if a website knows where or what country the user belongs to, it may be able to offer a different language of the same web page. As another example, if the website knows the user's location, it may present the user with some regional-based news, promotions, or advertisement. Traditionally, there are two ways for a website to obtain the user's location. The first is IP-based. The second is to use the geolocation API provided by Google. The IP-based location. So how it works, the website or the origin server first obtains the user's IP address by inspecting the incoming request. And then the website is going to look up a database based on the IP to find out where the IP is located. There are many databases available online, such as IP2Location, GeoIP, and DBIP. These two figures in this slide demonstrate one example, the IP 1.2.3.4. Both IP2Location and DBIP tells me this IP is located in Australia, Queensland, and somewhere in the city of Brisbane. The geolocation API is provided by Google, which can obtain a very accurate user location. So this is also a database that is built by Google based on its comprehensive user profile, and there is no public information how such database is built. There are some heresies Google can gradually sniff users' information by correlating GPS devices and by wall driving. However, both approaches has some disadvantages. So first, for the IP-based geolocation, the biggest disadvantage is there is no ground truth, or in other words, there is no way to verify the accuracy or the correctness of such database. For example, we looked up this IP address, which belongs to AT&T. So IP2Location tells me this IP address is located in the Washington State and in the city of Redmond. But DBIP tells me the same IP address is located in Illinois and in the city of Chicago. If we look at these two locations, we found these two locations has a distance over 2,000 miles. And even worse, we don't know which database is correct, and we don't even know if both databases are wrong. For the geolocation-based API, although it can provide a very accurate user information, it requires the permission of the user at the first place. For example, if a user first visits a website and the website wants to use geolocation API to obtain the user's location, the browser is going to pop up this dialog and ask the user if the user allows the location information to be shared with this website. Today, as users concern more and more about their privacy, it's very likely that a user won't allow a website to obtain this information. In this paper, we propose a novel approach which doesn't use IP and doesn't use the geolocation API, and we want to use the Content Delivery Network, or CDN. So first, what is a CDN? So CDN is a bunch of cache servers that caches web document and uses cache to serve client. For example, if my origin server is here and the client here want to request the document from the origin server, the request will first be sent to a edge server or a cache server. If there is a cache is stored in this edge server, the edge server is going to directly reply to the client without fetching a new document from the origin server. So the main function of the edge server is to cache a document from the origin server and use the cache to serve the client. But in the meanwhile, many edge servers will append a few response headers to the response when it serves a client. In this slide, we demonstrate one response header that is served by a CloudFront edge server. So all these headers are appended by edge server, and among all these headers, this header is of particular interest to us. So this header xamazon.cf-pop with the value dfw55-c1 indicates the ID of the edge server. And we have found that for many CDNs, it is very common to use this three-letter airport ID to indicate the edge server. So what we can find from this response header is that this response is served by edge server that is located at Dallas, Texas, United States, because DFW indicates Dallas-Fort Worth International Airport. So based on this fact, we got the idea to use CDN to infer a user's information. So the idea is like this. First, we assume that origin.com is a website that wants to infer users' information, and pilot.com is a website that uses CDN. So at the beginning, user is going to request, for example, index.html from origin.com. Origin.com is going to reply as is, but origin.com will also include a small JavaScript asks the user to fetch pilot.com. When this script is being executed, user is going to send a request to pilot.com. Because pilot.com is using CDN, this request will be served by a CDN, and the CDN edge server is going to append its edge server specific header. In this case, we assume it's DFW. Then the origin server can use some other ways like another fetch request to obtain the value of such headers. So then the origin knows that, okay, so this server is served by edge server close to Dallas, and then this server must also be somewhere close to Dallas. By this, the origin server can infer the user's information. In this paper, we conduct several experiments to validate the usability and accuracy of our approach. So first, we find not all CDNs are the same. There are some CDN that is very expressive. For example, Cloudflare, CloudFront, and Fastly, which are three of the biggest CDNs in North America, they all append some customer headers to indicate the ID, identity, and location of the edge server. And there are some other CDNs, such as the CDN provided by Google or by Microsoft. They do not append such informations. Therefore, in this experiment, we are going to use these three CDNs to validate our approach. So the first step is we want to find out how many edge servers these three CDNs has. So what we do is we conduct a live scan of all the IP addresses owned by these three CDN providers. So in this table here is the total IP address owned by Cloudflare, CloudFront, Fastly, which are available from their website. And we found there are this many live IPs. And at last, we gather all this response and we found out unique ID. So Cloudflare we cannot find out because it uses Anycast, but for CloudFront and Fastly we find CloudFront has 283 edge servers distributed in many cities around the world. Fastly has 78. And we want to find out whether our approach is effective, and here is what we do to validate it. So we purchase an account from ExpressVPN, which is a VPN service that has a total of 160 endpoints in 94 different countries. So we, here in the United States, we log in to each endpoint, and at each endpoint we send a request to a pilot domain that we know that uses Fastly, Cloudflare, and CloudFront respectively. And then we gather these three responses and we analyze the location-specific header from these three responses, and then we evaluate the granularity of CDN-based approach. So here is the information about this VPN. So in total, we were able to connect to 148 endpoints among these 160 that is claimed in its website. And in this map, we show all the countries where we are able to connect to a VPN endpoints. So these 148 endpoints located in 93 countries. And you can see most American countries and most European countries are covered. This slide shows our result. So we zoomed in to all the European countries because it is densely covered. This figure 4 shows the countries that are served by CloudFront. This is Fastly, this is Cloudflare. And we use different colors to indicate the countries that are served by different edge servers. So from these three figures, what we can find out, first, CDN edge server have a clear regional character. Okay, so different country or close by country are usually served by the same edge server. And also we can find different CDNs has different service regions. For example, in here, we can find out Cloudflare serves these three countries, which are Norway, Sweden, and Finland, using one edge server. But for Fastly and for CloudFront, they serve these three countries with different edge servers. So this page demonstrates the result when we combine the three CDN providers, CloudFront, Cloudflare, and Fastly. We have more detailed information in the paper if you're interested, but here to summarize, so for the 46 European countries using these three CDN altogether, we are able to divide them into 35 different regions. In other words, if a user is from somewhere in the European countries, we have high confidence that we can locate a user in one or two countries. This page demonstrates the state-level granularity. So for the VPN we have their endpoints located in this many states in the United States. And as you can see here, all different states have different colors, which means using these three CDNs, we are able to uniquely identify user in a different state. This page shows the sub-city level granularity. For the VPN we have used, it has 7 endpoints in the city of Los Angeles. And we log into each of these endpoints and we send requests to CloudFront, Fastly, and Cloudflare. And for the result, for these 7 endpoints, we can successfully differentiate 6 of it, except besides this one, Los Angeles and Los Angeles-3, they all have the same combination, but all other endpoints, they have different combinations of CloudFront, Fastly, and Claire, which means we can clearly and uniquely differentiate each of these endpoints. So to wrap up, in this paper, we proposed a novel approach for internet user geolocation. We do not rely on the IP address of the user, and we do not use the geolocation API provided by Google. Instead, we use a CDN edge server to find a rough or coarse-grained location of the user. And second, we run some practical experiments based on Cloudflare, CloudFront, and Fastly, and we leverage a commercial VPN which has 160 endpoints across the world to facilitate our experiment. And at last, our experiment demonstrated that the CDN-based geolocation is able to locate user to the country, to the state, or even in the sub-city level. That's our paper. If you are interested, you can read our papers for more details. Thank you.
Hi everybody, it's a great pleasure for me to speak here. The topic of my speech today is blockchain-based multi-keyword similarity search scheme over encrypted data. With the rapid development of computer technology and the Internet applications, the demand for data access and information storage is increasing. Cloud computing enables users to enjoy high-quality services, but outsourcing data to cloud servers makes data owners lose the control over their data, resulting data privacy disclosure. In order to protect the data privacy, data owners usually opt to encrypt their data before outsourcing to clouds. This in turn limits the availability of encrypted data. For example, the widely used keywords retrieval technology of plain text information cannot be directly applied to encrypted data. Therefore, some first proposed a searchable encryption scheme to fulfill the retrieval of encrypted data. The cryptographic model of the scheme is simple. There is no additional storage space overhead, but the search performance is limited by the size of the fields. Considering the problems of retrieval efficiency and security, much effort has been devoted to enabling search over encrypted data. However, the above schemes are based on the ideal assumption, that is, servers are honest but curious. In practice, servers may delete user data and perform partial queries or falsify search results to save computing and storage resources. Recently, there is some work proposing verifiable designs that enable the data owner to verify the correctness and integrity of search results and outsourced data. But the verification technique is highly dependent on specific search schemes. That is to say, it lacks a verification mechanism suitable for all search schemes. Besides, if the server doesn't return the value used to verify, or returns nothing, the user cannot determine whether the server is behaving correctly. So, to some extent, the server is still trusted. The characteristics of blockchain can prevent user data from malicious tampering and ensure the correctness of search results. This is because if the results are wrong, the server will be punished. Besides, it can resolve the search problem of existing blockchain systems and realize the data sharing. So, in this work, we propose a blockchain-based multi-keyword similarity search scheme over encrypted data, utilizing smart contracts in Ethereum to allow users of different roles to request access per million and interact with confidential documents. Table 1 shows the notations used in our manuscript. In Figure 1, we outline the architectures of our system. There are three entities in our system model: data owner, data user, and Ethereum. In order to protect the privacy of confidential documents, the data owner uses the symmetric encryption algorithm to transform them into ciphertext. Then it will be uploaded to the blockchain in the form of transaction. After the transactions are successful, each of them will have a corresponding transaction identifier. The owner uses these identifiers to generate an index and encrypts it. Then the owner uploads the index to the blockchain in the form of transaction. When the user queries the encrypted data stored in a blockchain, he or she sends the transaction embedded in the trapdoor to Ethereum. After receiving a search request from a user, the smart contract executes search algorithm with a search token, and the previously stored index and saves the search results to its state, which is publicly known, including the data owner. After receiving the search results, the user uses the secret keys to decrypt the documents. Depending on what information an adversary knows, we adopt these two threat models. The first one is non-ciphertext model. In this model, the adversary only knows the encrypted fields, the encrypted index, and the search trapdoor submitted by the user. It means that the adversary can conduct ciphertext-only attack. The second one is non-background model. In this stronger model, the adversary not only equips with the knowledge of non-ciphertext model, but also some other knowledge, such as the term frequency statistics of the document collection. Specifically, the adversary can conduct a term frequency statistical attack to infer or even identify certain keywords through analyzing histogram and the value range of the corresponding frequency distributions. Our design goals are soundness and privacy preserving. The former indicates that if there is a malicious server that doesn't correctly perform a protocol, it will get caught and obtain nothing. For privacy preserving, we aim to protect the index and query confidentiality, query unlinkability, as well as keywords privacy from adversaries. That is to say, the adversaries cannot infer the plain text information about the content of chapter and index, and cannot identify whether or not two chapters are from the same search request, and cannot deduce whether the specific keyword is contained in a chapter through analyzing the term frequency distribution histogram. The following are our design challenges and countermeasures. In Ethereum, each operation, including sending or storing data and executing computations, has an upper bound of consumed gas, that is, gas limit. This restricts the size of transactions and the complexity of designed functions. Therefore, we divided the encrypted data to make privacy-preserving search over a large database feasible. Specifically, the main challenge is to divide the traditional binary index tree into multiple sub-indexes. In Figure 2, you can see the process of index partition size due to the restriction of gas limit. The operation of access control may become expensive when there are abundant and complex expressions in a smart contract. Therefore, in order to simplify the whole access control mechanism and avoid the complexity of individual authorization, we introduce an effective rule-based access control strategy for transaction data. It can assert who have permission to access the requested transactions by checking whether the user roles are the root of the target polynomial. The detailed process is the data owner writes the access control policies, roles information, and permissions of the users to smart construct and store it on each node. The user searches the encrypted data by submitting the transaction that contains the trapdoor, the transaction identifier of the index, and its role information. After receiving the search request of the user, the smart contract executes the access control strategy in advance. For the access control process, we prove its correctness. Then we give a security analysis of our scheme in Section 5. In Section 6, we make an assessment for our scheme on 4 different datasets. We first provide a comparative summary of our proposed scheme and other blockchain-based searchable encryption schemes. As shown in Table 3, our scheme supports similarity search for the general data and novelly uses smart contracts to create an access control mechanism, having a certain advantage in terms of function. On the locally simulated Ethereum network, Table 4 presents the time overhead for building an index, uploading encrypted data, and generating a trapdoor on different datasets. We can observe from the experimental results that the overhead of uploading the encryption data to the Ethereum blockchain is much higher than other overhead. This is because data owners store their confidential data in blockchain by embedding it into thousands of transactions, and each transaction costs about 4 seconds on average. Besides, we compared the query time overhead corresponding to the change of matching document numbers on different data sets. As shown in Figure 4, the size of DB4 is the largest, with the longest time of searching. Accordingly, the query time overhead on the DB1 is the least. We explain that by a longer number of mined blocks leads to a longer time for loading, as shown in Figure 5. In the case where the number of accounts is determined, the access control decision time is evenly distributed around 0.4 seconds and doesn't change with the size of the dataset. As shown in Figure 6, we compared the search efficiency of our subindexes with traditional binary tree index. The experimental results reveal that the subindex structure is more efficient than the traditional binary tree index. Finally, we show the impact of the different P and K on precision in Figure 7. In a word, experimental results show the practicability of our scheme. In this work, our novelty is to use smart contracts to create an access control mechanism and fulfill multi-keyword similarity query. The possible further research direction is to establish a protocol that enables access control crossing the domain on the basis of the present work. Thanks for your attention.
Hello everyone, welcome to my presentation. My name is Song Liu. I come from the George Mason University. This work is done with the Qiang Song, Teng Song, and Qi Li. In this work, we use the SGX technique enhance the security of the single sign-on system to prevent credential leakage on the server side. Alright, this is outline of the presentation. First, we will briefly introduce the motivation of this work, and then we will give some basic background on the single sign-on system and the SGX technique. Then we will discuss the threat model and illustrate the design idea of SGX-Cube and how it be used to protect a single sign-on system. And then we will give the performance evaluation, and finally we will give a summary of our work. As we know, username and password are most commonly used user credentials for the authentication in the online login system currently. For the Internet service provider, it is very crucial to protect user credentials on both disk and memory. Constructing and maintaining a strong and effective defense system may cause overhead for the small companies and organizations. Some of them will choose to use the cloud service. Well, in the cloud environment, curious but honest cloud service provider have the privilege to capture the sensitive data in the memory. In this reason, more and more the Internet service providers start to turn to the single sign-on service, such as Google and Facebook. In this way, the Internet service providers no need to protect their user credentials anymore. For user, it also makes life easier. They don't need to remember a large number of the username and passwords. One is enough. However, there is a same problem. How to effectively prevent the credential leakage. Even in the last year, Facebook leaks the data of the 490 million users. So it is still necessary to find a solution to enhance the security of the single sign-on system. The single sign-on system provides an authentication process. It allows the user to access multiple application servers with one set of login credentials. A user only needs to log in once and then gain access to the different applications without re-entering the login credentials at each application server. As a third-party authentication system, the single sign-on system is trusted by both end user and a number of application servers. One single sign-on system consists of the three main parties: the identity provider, the relying party, and the user. The identity provider, the IDP, is responsible for providing authentication services. Well, the relying party, RP, are the applications or websites to be accessed by the users. The user will verify his credentials on the IDP. After successful verification, IDP will allocate the token to both the RP and the user, so the user can use the token to present himself the identity on RP to access the desired applications or websites. Intel SGX provides user-level isolation execution environments called SGX-Enclave to protect the confidentiality, integrity, and freshness of the application code and the data in a reserved memory. This memory area is called Enclave Page Cache (EPC). The data in the enclave is transparently encrypted. Only the CPU is trusted. SGX can protect an application against illegal access from other applications, OS, hypervisor, and firmware. Since Enclave is running in unprivileged, it cannot harm the system. The maximum EPC size is limited. For the SGX version 1, its size is 128 MB. When configured, enclave size is larger than EPZ size, the performance overhead becomes inevitably high due to the paging between the EPC and the normal memory. The active thread running at the same time inside the enclave is limited by the number of the logic CPU cores, since SGX thread keeps occupying one logical core unless it ends or exits the event head. In the threat model, we assume the attacker can conduct both offline attack and online attack. In the offline attack, the attacker can extract credential database from the disk. He can use the public information to infer the sensitive data. And he can also brute force the encrypted credentials from the database. In the online attack, the attacker may retrieve the plain-text credentials by eavesdropping the communication channels, connect to the authentication server, monitoring the memory of the server, manipulating the login requests, or creating the known plain-text records in our database to launch the chosen plain-text attack. If it is the result list to reveal the desired credentials, the attacker may try to circumvent the authentication process by manipulating the authentication process in the memory or splitting the stored credential records. In this work, we assume that Intel SGX can be trusted to protect the code and the data in enclave. As shown in this figure, like the standard single-cell scheme, our SGX-Cube is divided into the three main components: identity provider, relying party, and the user. These three components interact with each other during the complete login procedure. As the key components of the single-cell system, the IDP consists of the two main components: the enclave-based authentication server and the credential database. The authentication server runs inside enclaves. It is responsible for conducting remote attestation, receiving the user login credentials, verifying the user login credentials against the credential database, generating an authentication token, and then allocating the token to both clients and facilitate the authentication of the client to the application server. We're splitting the authentication server into the two modules, into the separated enclaves, the response module and the authentication module. Splitting the authentication server into these two enclaves, we intend to mitigate the risk of the credential processing by isolating the authentication module from the potential vulnerabilities of the network interactions. The response module is established a secure communication channel with the application server and client to defeat the eavesdropping and the tampering. It handled all the requests from it. The authentication module processes the credential-related tasks. The credential database stores user credential information for the user authentication. The RP could be any kinds of the auth and the shift application server on the internet. Without verifying the user credential by itself, it trusts the IDP. In our design, the user should get a seamless, out-of-the-box, easy-to-use client. The client could be a typical browser or the self-developed application that supports the single-cell scheme. Before the application server accepts a login request, it is necessary to ensure the IDP is trustworthy. RP needed to conduct the attestation to verify the enclave is running on the real SGX-enabled platform, and the authentication server code is running inside the enclave was not tampered with. To ensure the trustworthiness of the IDP, the application server could start the attestation periodically, for example, 24 hours once. Otherwise, the attestation could be conducted by a trusted third-party CA. The application server only needed to verify the certification of the authentication server. Now, we introduce the login procedure. Our work follows the OAuth 2 standards. Stage 1. Login request. In this stage, user uses his browser to send the login request to the web server. The web server will return the redirection URL and help the browser to redirect to the IDP. The IDP will check the client request and then return with the login form page to the user. Stage 2. Credential handling. After receiving the login form page, the user will be typing into their credentials, and this credential will be sent to authentication server. Authentication server will be check the credentials. If they pass the verification, it will be allocate authorization code and the redirection URL to the user again. Stage 3. Authorization granted. In this stage, the user will be resend to the authorization code to the web server, that is RP. And this RP will be send the authorization code and his client ID and the client secret to the authentication server again. The authentication server will be checked this authorization code and finally generates the access token. This access token will be sent to the web server. Stage 4. Service access. After get access token, the web server can resend the access token to the authentication server to request the user information. The user information will be help the web server to identify the user, and the web server will be allowed the user the tokens and web resources to the user. After that, the user can freely to access the web server. In the credential database, we store the 3 columns of data: username, password, and user information. Each column has a unique subkey. The user information stored in the credential database could be the username or other information, for example, email, an address used in the application server. It is an identity of the user for the application servers. In our scheme, all 3 columns are encrypted, which increase the entropy of the user credentials against the brute force attacks. We bind the username into both the password and the user information to eliminate the possibility of the failed substitution. This is also equivalent to protect each record with the different key. The username and the password are protected with HMAC, while the user information is all encrypted, since the authentication server will decrypt the user information and send it to the application server. Under the offline attack, the encryption scheme of the credential database will guarantee the data confidentiality. The unique subkeys sealed on the disk will increase the difficulty for the brute force. Under the online attack, we are set up the secure communication channel and use SGX encrypt credential in the memory, which can guarantee the data confidentiality. And also SGX protects the data integrity, and the record-based encryption defines the splicing attack, so we also can protect the data integrity under the online attack. We measure the performance of authentication server in each stage. From the experimental result, we found the stage 1 has the highest time cost. That's because the authentication server sent a complete HTML login page to the user in this stage. Although we only implement a very simple login page, it's still the largest size of the data to be sent in all 4 stages. In the stage 2, since the authentication server needed to interact with the credential database, so we can see the overhead is the second highest. In the stage 3 and stage 4, the authentication server locates the required information and responds to the corresponding request, so the time overhead is relatively low. Compared with the vanilla single sign system, our work is increased about 0.6 times in the time cost. We also measure the overall performance of our work. The results show us a complete login procedure costs about 11,500 microseconds for a single authentication server thread to handling a single request. The percentage of the authentication server overhead is about 14% in the overall overhead. Our testbed overheads the 4 logic cores. When the number of the threads exceeds the number of the logic cores, the extra thread will be set idle. So with 23 threads, the performance will not be improved in our testbed. A summary: we designed SGX-Cube to leverage the SGX technique and the record-based encryption scheme to protect the user credentials on both the memory and hard disk on the server side. SGX-Cube can be ported onto the various application servers by the following OAuth 2 standard. An SGX-Cube can effectively protect the confidentiality of the login credentials with a small performance overhead. That's all of this presentation. Thank you.
everyone. Thank you for attending the session. My name is Dalton Hahn, and I'm a current PhD student at the University of Kansas within the Electrical Engineering and Computer Science Department. And on behalf of my co-authors, today I'll be presenting our work titled MisMesh, Security Issues and Challenges in Service Meshes. So to begin with, service meshes are an emerging area of the DevOps toolset and the DevOps ideology, and they're primarily used to collect and manage clusters of microservices. However, despite broad industry adoption of service meshes, they do lack a thorough, peer-reviewed security evaluation. And today in this presentation, we will consider evaluating service meshes both from an idealized administrator, or one who has a deep knowledge and understanding of the available security mechanisms offered within service meshes, as well as how to properly and optimally configure those security mechanisms, and we'll compare that with the default security offerings of the tools. Now to begin with an outline, today we'll cover background and motivation for the DevOps ideology. We'll consider a unique threat model to the service mesh domain, and then we'll examine our experimental evaluation under the idealized or deep knowledge administrator case, and we'll compare that with the default offerings in these state-of-art service mesh tools. Now, to begin with some background, there's currently a shift occurring in software engineering design for large enterprises. Large enterprises are often moving away from these large monolithic software applications, which may be difficult to update or manage dependencies and errors that propagate across the system. And they're moving towards a microservice architecture of small, indistinct components that collaborate well at scale, are easier to update, fix errors for, and are able to be rolled out quickly. Now, Kubernetes, Docker, and HashiCorp Nomad, as well as many other tools, are designed to deploy and scale these microservices quickly, and then they leave service registration, service discovery, and service configuration of those microservices that have been deployed to later tools such as Istio, Consul, and Linkerd version 2, which are considered service meshes. And these address those issues of registration, discovery of services, and configuration of those services in a coherent manner. So to provide an example of a few different service mesh architectures, first we'll look at Consul. So on the left-hand side of your screen, you will see the Raft election protocol. So at the beginning of Consul cluster creation, privileged members of the Consul cluster titled Consul servers undergo an election process to elect a leader of the cluster who is responsible for maintaining log coherency across the entire cluster. And then moving towards the middle of your screen, cluster operation is depicted as well as the Consul quorum, or the privileged group of members within the Consul cluster. So being Consul servers, they are responsible for maintaining log coherency across the entirety of the cluster. And then underneath is depicted two Consul clients, one in the cloud and one on an arbitrary virtual machines platform. And these Consul clients primarily host the services that actually do work within the service mesh. So here it's also pointed out cluster communication and service-to-service communication. Cluster communication is primarily membership information passed among members of the cluster. So this is information about whether a particular node is alive, what services they have available, and simple registry information. And then the service-to-service communication that occurs between nodes within the cluster is the actual work of the service mesh. Things like if you're hosting a web service or a database service, those requests and fulfillments of requests are passed in the service-to-service communication channels between nodes. Lastly, on the right-hand side of your screen, you'll see the service membership protocol. And so depicted here is the three Consul servers that are part of the Consul quorum. And between these nodes of the quorum are heartbeat messages that are exchanged that denote whether or not a node is alive, whether or not they are a member of the cluster, things like that. So comparing that architecture with the architecture of Linkerd version 2 or Istio, on the left-hand side of your screen is the depiction of a standalone Kubernetes cluster. So the standalone Kubernetes cluster is a star topology-like system that is controlled and managed by a Kubernetes master that may be remote or on-site. And the Kubernetes master is responsible for maintaining cluster membership, encrypting messages at the cluster level, so between node to node, and then providing cluster access control mechanisms. Next, on the right-hand side of your screen, you'll see the Linkerd version 2 overlay that occurs on top of a Kubernetes infrastructure. And this is very comparable between Linkerd version 2 as well as Istio. They operate on top of an existing Kubernetes infrastructure, and Linkerd version 2 as well as Istio are primarily responsible for encrypting service-to-service messages, performing traffic shaping, and service-level access control. So access control between services, as well as encrypting service-to-service communication rather than cluster membership communication. So next we'll consider our threat model that's unique to the service mesh domain. So similar to many other threat models, we consider the adversarial goals of disruption of service, as well as manipulation, exfiltration, or injection of data within the cluster. So for example, keys or passwords and other things may be stored within the cluster itself. And so exfiltration of that data, manipulation of that data, or injection of false data within the cluster's storage system would be an adversarial goal. Additionally, we consider the unique adversarial goal of infiltration of the cluster or takeover of the cluster to a position of privilege where an adversary may have more resources at their disposal by controlling other members of the console cluster as well, and doing things like larger scale distributed denial of service or manipulation of cluster architecture to the point where they can reroute services, inject malicious configurations, or other potential options. So we classify these high-level goals as disruption, manipulation, and takeover. So considering our idealized administrator, or one with deep knowledge of the available security mechanisms of these systems, we use Consul as a representative service mesh for our experimental evaluation. And the reason for that is Consul currently has the largest number of GitHub contributors, as well as a comparable number of GitHub repository stars to the runner-up tool being Istio. And we then conducted our experiments on hardware systems that are comparable to those that may be found on-site in data centers or in cloud data centers. And then we provide a sampling of the experimental attacks in this presentation, but for more detailed examples, as well as further details of the attack procedures, those can be found in the paper. So first, we'll consider data center as a label as the sole mechanism of defense enabled within a cluster. And you can see that in all four scenarios, all adversarial goals are able to be achieved. And the reason being, when using data center label as a secret as the sole mechanism of defense within the cluster, you can see down below that node 1 would simply add this parameter to their configuration and then execute that. And in communication with node 2, this parameter appears in plain text in every packet that is exchanged between node 1 and node 2. And so therefore, should an adversary be capable of collecting even a single packet occurring between any node in the cluster, they could then extract the plain text data center label and then use that in their own configuration to maliciously take action within the cluster. Next, we'll examine UDP key storage, or the UDP encryption mechanism, as the next sole means of defense. And so you can see that under UDP encryption, unprivileged threat are unable to accomplish any of their goals. So if they are not able to compromise a node within the cluster, none of their adversarial goals may be achieved. However, should any singular node within the console cluster ever be compromised in the lifetime of the cluster, then all adversarial goals are capable of being achieved from any position. And the reason being is that console has a shared singular UDP key for the lifetime of the cluster, and that shared UDP key is actually stored in plain text on disk. And so should any node within the cluster be compromised, the adversary could simply read that key from disk, use it in configurations, or replicate that key to other malicious members and take larger actions within the cluster. Next, we'll consider access control lists as the sole mechanism of defense. And under access control lists, as you can see, in all four scenarios, the adversarial goal of disruption is able to be achieved. And the reason for that being is that as console processes requests under an access control list system, they process each of those requests to check for legitimacy. And so in doing that, external members that are not external parties that are not members of the console cluster, those messages must still be processed to check for legitimacy. So on the left-hand side of your screen, you'll see a stable quorum state, and this is quorum members exchanging consensus messages, maintaining log state, and operating in the benign setting. And then on the right-hand side of your screen, you will actually see the instability of the console quorum under attack or under stress from external members. So in our experiments, 25 attacker nodes were necessary to throw the quorum into a state of instability. And the reason for that being is when 25 of those attacker nodes attempt to execute a join operation where they have no privilege within the cluster, those messages must still be processed, taking up resources from the quorum, and by taking up those resources, the normal benign consensus messages are unable to be sent and unable to be received, and the quorum enters a state of instability. So next, we'll consider the default offerings of service meshes. And first, we'll look at console. So examining the default availability of console security mechanisms, you can see that all mechanisms being cluster message encryption, service message encryption, cluster access control, and service access control are available in the tool, as well as in 3 of the 4 mechanisms, revocation of those security materials are possible. However, you'll then note that by default, none of these mechanisms are enabled, and in 3 of the 4 cases, the default lifetime of the security materials is unrestricted, and there's no redistribution mechanism to maintain freshness of those security materials within the cluster. Next, we'll examine Linkerd version 2 in conjunction with an underlying Kubernetes infrastructure, as described earlier. And as you can see, in the case of service message encryption, Linkerd version 2 not only has the capability of that security mechanism within the tool itself, it also enables it by default with a default lifetime of 24 hours and provides revocation and redistribution of certificates that enable service message encryption. This denotes a very nice design decision in Linkerd version 2, as well as a very flexible and dynamic security mechanism for the DevOps environment. However, you'll notice that by default, the remaining mechanisms are not only lacking in Linkerd version 2, but they are also not enabled by default in Kubernetes either, and so Linkerd version 2 lacks any of those mechanisms in a production state under the default scenario. Additionally, you'll notice that Linkerd version 2 inherits the service access control mechanisms of Kubernetes. And so if the service access control mechanisms are not enabled or configured properly within Kubernetes, Linkerd version 2 inherits those flaws by default. Next, we'll look at Istio in conjunction with Kubernetes. And very similarly to Linkerd version 2 and console, all mechanisms of defense lack enablement by default within Istio and Kubernetes. And additionally, the same issue of inheriting the lack of service access control by default from Kubernetes occurs here within Istio as well. So to conclude this presentation, we present the first experimental security evaluation of state-of-the-art service mesh tools. We considered an idealized administrator, or one that had a deep knowledge and a deep understanding of the available security mechanisms within these tools. And even despite optimal configurations of those tools, within 10 of 20 scenarios, complete cluster compromise is possible, meaning all adversarial goals are able to be achieved. And in an additional 5 scenarios, at least one of those adversarial goals is achievable. We then compared the idealized experimental results to the default security offerings of the 3 most popular service meshes, namely being Console, Istio, and Linkerd version 2, and we found that all studied tools except for Linkerd version 2 fail to enable any of their security mechanisms by default and often lack revocation or redistribution mechanisms for those security materials, showing a distinct design flaw and a contradiction between the DevOps methodology and ideology of dynamic systems and long-living security materials that are present in these service mesh tools. So once again, thank you for your time. Thank you for attending the session. If you have any questions, please feel free to contact me or my co-authors, and we would be happy to address those issues. Thank you.
Hi everyone, I am MD Mazhar Islam from University of North Carolina at Charlotte. My other colleagues Dr. Ihab Al-Shai from Carnegie Mellon University and Basit Rahim from UNC Charlotte. Today I will present our paper, Email Address Mutation for Proactive Deterrence Against Lateral Spear-phishing Attack. Email spear-phishing attack is one of the most devastating cyber threats against individual and business victims. Spear-phishers can impersonate authoritative identities in order to incite victims to perform actions that help them to gain financial and hacking goal. Recent report shows that 90% of data breaches in 2017 and 2018 include a phishing element. 74% of public sector and 64% of organizations attack involve spear-phishing attacks. 71.4% of phishing attacks and data breaches in the United States used spear-phishing. The FBI reported that only in 2019 over $26 billion has been lost to spear-phishing and account takeover. Unlike phishing, where adversary sends generic emails with malicious attachment or links to a massive number of users indiscriminately, hoping that someone will take the bait, spear-phishing is more targeted. Many of these spear-phishing cannot be detected based on analyzing email because they can be sent from compromised benign accounts. This special type of phishing is known as lateral spear-phishing attack. To make the attack trustworthy and effective, adversaries carefully choose those compromised accounts that are closely related to the victim, such as employees from the same organization. Lateral spear-phishing attacks are very hard to detect because of the cleverly crafted content created by deep analyzing the prior conversation with the victim. In lateral spear-phishing, adversaries inherently defeat the defender by evading any existing security regarding sender authentication, as the email is coming from legitimate account, and defeating behavioral anomaly detectors by accessing human anchoring, as the email seemingly composed by a trusted entity. Here is an example of lateral spear-phishing attack. Adversary Trudy compromises the email account of Alice, CEO of an organization. By examining her inbox, Trudy obtains that Alice directed Bob to make some wire transaction for arranging an upcoming business meeting. Exploiting this analysis, Trudy composes a phishing email from Alice's email account to Bob asking him to make a wire transaction to Trudy's bank account. This type of lateral spear-phishing are crafted carefully by observing previous emails and may not contain any malicious attachment or URL that make it very hard to detect. Existing literature that detects lateral spear-phishing attacks, such as behavioral anomaly-based detector, uses distinct attack signature, for example, malicious URL or attachment, and features for header or content analysis. However, they require large historical dataset for training and often subject to high false positive and false negative rates. They fails to detect lateral spear-phishing attack because lateral spear-phishing attacks mimics benign user behavior. They can avoid bad signatures, and they composed from legitimate email accounts. Therefore, standard email spoofing detectors such as SPF, DKIM, DMARC fail to detect lateral spear-phishing attack. Other cryptographic approaches such as PGP and SMIME can ensure sender authenticity by digitally signed or encrypt the email. However, they are not widely used because of low usability. It requires end user to use public key cryptography. The users often requires training to use PGP tools. They also have very low transparency. For example, PGP encrypted ciphertexts immediately lose the visibility from the plain text, which often prevents using other technologies such as IDS. Recent studies shows that PGP signatures can be spoofed as well. Therefore, we developed a novel proactive defense technique using sender email address mutation to protect a group of related users called VIP users from lateral spear-phishing attack. In our approach, we change the sender email address randomly while forwarding an email that can only be verified by the trusted peers. A secure gateway in the cloud do the mutation and verification transparently between end users and email service providers. It does not impose any overhead or restriction on email communication with external users. Email mutation technique is transparent, secure, and very effective. It allows users to use their email as usual while they are fully protected from lateral spear-phishing attack. Here's an example to understand the email mutation protocol. For example, Alice and Bob from same organization decided to use email mutation, so we call them VIP users. There is another user, Ron from enterprise.com, who is not in the list, hence known as non-VIP users. Before the mutation starts, they use their real email addresses as regular to communicate with each other. We call such communication real channel communication. However, when the email mutation starts, each of the VIP user receives a set of shadow email addresses. For example, Alice gets n number of shadow email addresses and Bob receives m number of shadow email addresses. Now, when Alice composes an email to Bob, instead of using her real email addresses, one of her shadow email address is used as sender email addresses. Similarly, when Bob sends an email to Alice, one of his shadow email addresses is used as sender email address. So what is a shadow email address? The shadow emails are a list of pre-created email accounts assigned to all VIP users but being kept hidden from them. These accounts are only used in email transmission as a sender address. Only the email mutation gateways conduct with these email accounts. Depending on the impacts, the number of shadow email addresses assigned to a VIP user varies. A possible shadow email address may look like real email address.x, where x is at least 16-byte long random alphanumeric sequence. There is an example of Alice shadow email addresses. In the email mutation architecture, we have two components. One is the email mutation agent that resides in the client environment. All the devices a client may use to access their email account must have an email mutation agent. Another component is the central email mutation gateway, which resides in the clouds. Now let's see the workflow of email mutation system. Alice wanted to compose an email to another VIP user, Bob. The email goes to the mutation gateway through the email mutation agent. In the gateway, the real email address alice@org.com changes to one of her shadow email addresses, and then it forwarded to the mail server. When Bob wanted to fetch a new email, the email first go to his mutation gateway. Inside the gateway, the shadow email address gets verified. If the verification is successful, the gateway translates back the shadow email address to the real email address and forwarded it to the agent. The agent then delivers the email to the client. Here is the algorithm that how a shadow email address gets selected for both mutation and verification. When a VIP user sends an email to another VIP user, their last L number of email communication between them is used as ground truth. The ground truth is hashed to generate a mutation ID. By indexing the mutation ID, a shadow email address gets selected from a secret arrangement of shadow email addresses assigned to that sender. Now let's see how email mutation system identifies a lateral spear-phishing attack. Assume that TrueD compromises one of the VIP user's Alice email account. Now TrueD can do the following two cases to compose a phishing email. In case 1, TrueD directly sends an email as Alice to Bob. In case 2, TrueD guessed there is an email mutation going on and now she wanted to assume or randomly guess one of Alice's shadow email address. In either case, the email first goes to the mail server. When Bob wanted to fetch that email, it goes to the email mutation gateway first, where the mutation gateway sees that the sender address is coming from either directly from Alice's account or it is a random guess of shadow email addresses. However, adversary TrueD doesn't have Alice's secret shadow email addresses, so the guessing address is not correct. Therefore, the mutation gateway identifies the email as threat. Then the email gets discarded. To optimize the overall communication with external users, email mutation do not do any mutation when a VIP user sends an email to a non-VIP users. Similarly, no verification happens when a VIP user receives an email from a non-VIP users. Building such a solution is very challenging. For example, does multiple shadow email accounts requires any extra storage? The answer is no. Shadow email accounts only uses for sending emails. The receiver email address will always be the real email address where all the emails goes. Email mutation gateway uses IMAP append command to populate the real email sandbox to keep track of a successful delivery of an email between two VIP users. Email mutation doesn't impose any usability issues because it is completely transparent to end users. And it is very easy to use. It doesn't require any user training. For example, the system only adds a button in the client environment to forward an email with mutation. It is easy to integrate because email mutation doesn't change the email in the client environment. Email mutation is not vulnerable to insider attack. To understand what is an insider attack, let's assume that John is a VIP user who stole Alice's email account credential. Then John uses his email mutation agent to send a phishing email to Bob by impersonating Alice. To solve this problem, every VIP user's agent is synchronized with its corresponding mutation gateway instance through a unique authentication token. That means John's agent can only get instance of his mutation gateway. Therefore, it will only work for John himself, not for Alice or Bob. The system doesn't cause any privacy violations. For example, the gateways does not keep any copy of the email. The mutation agent connects with the gateways through secure channel such as SSL or TLS to defend against any man-in-the-middle attack while transmission. The secret shadow email list cannot be retrieved from the gateways. Secure email gateways are becoming very popular these days. Therefore, many organizations are adopting cloud-based secure gateways, including Cisco, Microsoft, Barracuda, Mimecast, and more. Email mutation gateways are consistent. For example, if a VIP user deletes any email from his sendbox or inbox that was sent by another VIP user, then the ground truth between them becomes asynchronous. To solve this problem, email mutation gateway keeps the hashed digest of the last L number of emails between two VIP users. Sender and receiver gateways perform this hash storing operation asynchronously while sending and or receiving an email. Therefore, they do not need to communicate with each other. Email mutation is a new technique, therefore it is necessary to ensure the design correctness. We use UPAL model checker to formally specify, model and verify the system to find any unknown behavior. We modeled email mutation using timed automata and verified against the following temporal properties. The first one is reachability, which describes that every good state is reachable and every bad state is unreachable. The liveliness describes the system is progressing to achieve a specific goal. And the deadlock freeness ensures that the system is not stopped and it is always progressing. We evaluate our email mutation system on various aspects. For example, the lateral spear-phishing and spoofing identification rate, the overhead added to the system, the brute force approach to break the email mutation system, and detecting other attacks such as integrity violation attack or man-in-the-middle attack. In our experiment setup, we protected more than 5,000 VIP members over 5 different organizations. The NASA Jet Propulsion Laboratory Red Team sends more than 500,000 attack emails. The VIP members use different types of email service providers such as Gmail, Microsoft Exchange, Apple iCloud, and so on. And they use different kinds of email clients such as mail.google.com, Outlook, Thunderbird, and more. Here is the output of the detection results. The lateral spear-phishing and spoofing detection rate is 100% for all values of shadow email addresses. Although we developed email mutation system to detect lateral spear-phishing and spoofing attack, we checked our system with other attacks such as man-in-the-middle attack. We showed that the integrity attack can be detected with 99% accuracy by using 100 shadow email addresses for a VIP user. Here's the attack detection results. The details can be found in our paper. We evaluated the shadow email address selection time against different email size. We showed that the delay is between 3 to 7 milliseconds for email size 7 to 12 megabyte. We evaluated the mutation overhead compared to the end-to-end email forwarding delay. For example, email size 7 to 12 megabyte, mutation delay is 4.5 milliseconds and the overall sending time is 1.5 seconds. Thus, the mutation overhead is 0.5% compared to the end-to-end email forwarding delay, which is very negligible. Using the similar technique, we calculate the verification overhead. We showed that the emails having 7 to 12 megabyte size have overall 10 milliseconds receiving delay, where the verification delay is 7 milliseconds. We measured the overall performance of an email mutation gateway by sending more than thousands of emails at a time to a single mutation gateway. While dealing with 5,000 emails per second, the average processing delay for mutation is 1.1 seconds, and for verification is 10.9 milliseconds. We evaluated brute force attack to break email mutation system. Adversary may try to phish by randomly guessing a shadow email addresses. However, guessing a 16-byte alphanumeric string is very hard. Therefore, we inform all valid shadow email addresses to the red team prior to launching the attack. It takes more than 14,000 tries for an adversary to phish a VIP user having 100 shadow email addresses. We showed that increasing number of VIP members or organizations do not impose any overhead into the system. The delays only increased when the total number of emails dealt at a time increases. In conclusion, the existing spear-phishing detectors are limited on using email contents for specific features such as malicious attachment or URLs. However, we presented a novel approach using sender email address mutation to proactively defend against the most devastating and stealthy spear-phishing attack called lateral spear-phishing. Our system guarantees that phishing emails sent from trusted users will be detected immediately. Email mutation techniques well integrated with existing email infrastructure, and it requires no special handling by the user. It requires an agent to be deployed on the client side and a central gateway in the cloud. We implemented and evaluated our system in large-scale real-world enterprise network with well-known email service providers such as Gmail. Our evaluation results showed that it caused only 0.5% overhead on overall email transmission, which is very negligible. Moreover, we showed that it is very hard to break the mutation system through brute force attack. The email mutation system has some limitations as well. For example, it cannot protect users if their physical machines get stolen. Another one is VIP users needs an agent instance for every single device they use. In future, we want to enhance our system to protect users if their physical device gets stolen. And we want to leverage our system in the server side to remove the use of email mutation agents. Thank you.
Hello, and welcome to my presentation on Bypass, Reconsidering the Usability of Password Managers. I'm Elizabeth Stobart from Carleton University in Ottawa, Canada, and my co-authors in this work are Tina Safei, Amr Youssef, and Mohamed Manan from Concordia University in Montreal, and Heather Molyneux from the National Research Council of Canada in New Brunswick. The problems with passwords are well known and intimately familiar to all of us. Passwords are difficult to choose, hard to remember, and frustrating to keep track of. One solution to these password problems is to use a password manager, a program that generates, stores, and fills passwords. A variety of password managers are commercially available and provide various features to help users manage the difficulties of passwords. By grouping all of a user's passwords together in one place, password managers can become a single point of failure for an end user. Password vaults are typically protected by a user-chosen master password, which suffers from the same vulnerabilities affecting other user-selected secrets. Other functions built into password managers can also become vulnerabilities, such as autofilling passwords or having passwords accidentally left in the paste buffer. However, password managers can also improve user security. When users use a manager to generate random passwords for their accounts, resistance to guessing attacks is improved. And password managers can also protect against some kinds of phishing and social engineering attacks. Although generally thoughtfully designed, adoption of password managers is low. End users are often unaware of password managers and uncertain how they work. They also tend to be concerned that the process of setting up a password manager will take too much time and effort. Even among people who already use password managers, they often don't use them effectively, and particularly, they often don't use the password generators to create their passwords. Users need to be actively encouraged to install and trial password managers, but even then, they often don't continue using them. One finding from work examining usability of password managers is that password manager workflows need to be completely rethought. So, in this work, our question was, how can we design a password manager to improve usability and increase adoption while maintaining or improving the security of the manager? Almost all password managers are set up in the same way, as client-side software based on a wallet model. The user unlocks the manager using a master password, which gives them access to a list of saved credentials. The basic interaction between users, password managers, and websites is also similar. The password manager is placed as an external resource available only to the user. Features might be provided to smooth the process of copying and pasting usernames and passwords from manager to website, but all interaction with the website happens exactly as it would if a password manager were not used. Many of the usability problems with password managers result from this setup. Copy and paste errors, leakage of passwords to the paste buffer, and form fills to the wrong field all result from placing the manager as an external resource, available only by the user and not by the website. Our insight is that many of these problems would be reduced if the password manager could communicate directly with the website. Why is a human in charge of copying and pasting strings from one computer program to another? We designed Bypass, our novel password manager, to address these problems by enabling direct communication between the password manager and the website. Bypass sits between the user and the website, allowing it to pass credentials directly to the website. This avoids errors and overhead resulting from user interaction with web forms that aren't designed to work with password managers. Using the provided API, the password manager securely passes credentials and can also request information, such as the password policy, from the website. In order to gain these advantages, websites must implement the Bypass API to be used with Bypass. This is admittedly a strong requirement, but we hope that the usability and security benefits of Bypass will encourage websites to implement the Bypass API. For websites where the API is not available, Bypass is designed to be backwards compatible and works like traditional password managers in that situation. For the remainder of this presentation, though, I'll be discussing fully featured Bypass, including the API. Moving the password manager to sit between the user and the website allows the majority of password and account-related interactions to be moved into the password manager instead of the website. This setup affords novel features, which include nudges towards secure randomly generated passwords. Bypass is able to request password policies from websites and automatically generate suitable random passwords for each account. Users can view and edit those passwords if they wish, but the manager is designed to make auto-generated passwords the default easy choice. Direct account creation. Users can create accounts on websites directly through the password manager, avoiding the back and forth of creating an account in the password manager at the same time as one on the website. Direct account logins. To log in to existing accounts, users can simply press the login button from Bypass, which sends their credentials and opens the website without any interaction with the login page. Password changes. Users frequently avoid changing their passwords, and password changes are particularly frustrating to password manager users who must handle copying and pasting multiple mask strings into the correct forms. In Bypass, password changes are made trivially easy, since the manager sends the new password directly to the website. Bypass also offers an automated password change option, where the password is changed at a regular interval. Account deletion. Another opportunity afforded by the Bypass architecture is to easily delete accounts directly from the password manager. Currently, account deletion is often made difficult by web designers, but privacy rights indicate that this should be an available option for users. We created a prototype implementation of Bypass for use in this work. This implementation has two components: the local password manager on the left and the server-side API on the right. The password manager was created as a Chrome browser extension that uses IndexedDB to store data. We used a REST API to communicate with the websites, and API calls are made via HTTPS using JSON. The prototype API was written in C# using the .NET framework. For this work, we also constructed two fictional websites to be used in our usability evaluations, and these both implemented our API. These details are specific to our prototype, but Bypass is designed to work with a wide variety of website setups. The API is packaged as a library to be included by web developers, and the manager is database agnostic. One consideration in creating our prototype was, of course, security. In our implementation, we chose to store passwords in an offline database, encrypted with AES 256, using a key derived via PBKDF2 from a master password and a random salt. This is equivalent to what is done in most commercially available password managers. We use TLS for all communication between Bypass and the websites to avoid remote network attacks and SSL stripping attacks. The direct communication of credentials that happens in Bypass also affords security benefits. All attacks resulting from copying and pasting, such as leaking passwords to the paste buffer, are avoided, as are autofill vulnerabilities. Ultimately, though, our goal in creating Bypass was to improve the usability of password managers, and we wanted to explore how users understood and thought about the features in Bypass. Would they be confused, since Bypass doesn't necessarily work similarly to existing managers, or would they find the features intuitive and easy to use? We conducted two separate usability evaluations, an early inspection-based evaluation called a cognitive walkthrough, and later a user study with a more developed prototype. After creating the first prototype implementation of Bypass, we wanted feedback on the usability of the manager. At that point, the prototype included the main functions: adding accounts, logging in, and a version of password changes, but was not sufficiently functional for a user study. We chose to conduct a cognitive walkthrough because of its focus on learnability and because it allowed us to include the perspective of novice users. We conducted a pluralistic walkthrough with 5 evaluators, the 2 project leads, the developer, and 2 independent usability experts who had no other involvement with the project. One of these experts was a longtime password manager user, and the other had no password manager experience. Neither was an expert in security. In our cognitive walkthrough, we were interested in whether Bypass would make sense to users, and we found both success and failures. The early prototype of the manager was deemed confusing and in need of stronger markers of flow, particularly to show users how to get started and what to do first. However, participants spoke to the intuitiveness of the Bypass account management feature set. In particular, we were interested in how the participant who was knowledgeable about password managers would react to features such as the one-button login, but he didn't comment until specifically questioned. When we did bring it up, he told us that it hadn't occurred to him to question how it worked, because it just worked the way he expected. Following on the cognitive walkthrough, we redesigned and re-implemented the Bypass prototype to create the version described here. Following that process of improvement and redevelopment of the Bypass prototype, we conducted an evaluation to investigate the usability of bypass with unbiased users. We chose an in-lab study so that we could observe participants' interactions with bypass and ask follow-up questions about their experience. Each study session lasted between 30 minutes and 1 hour and was divided into 3 parts. Participants first completed a pre-test questionnaire asking about existing password habits and demographics. After that, we provided them with a short introduction to password managers and a brief overview of bypass. They were asked to complete 6 tasks using bypass and then to complete the post-test questionnaire. In the study, we attempted to mimic a first real experience with bypass, but participants were provided with fictional account information to use in the study and did not use any of their personal account information. Our study was approved by the Carleton University and Concordia University Research Ethics Boards. There were 20 participants in our study, of whom 12 self-identified as female and 8 as male. They were recruited from university communities in Montreal and Ottawa and aged between 18 and 46. On average, they were quite young, with a median age of 24. 18 of them were students and 2 were university employees. 15 of them reported previous experience with password managers, and 3 of them reported that they were currently using a password manager. We evaluated the usability of bypass using 3 measures: efficiency, effectiveness, and satisfaction. We evaluated efficiency using the time spent on each task. For effectiveness, we assessed the number and types of errors that occurred during the study, and for satisfaction, we considered findings from the Likert scale questions. We also recorded observations related to task completion, participants' comments, problems, and recommendations. Times were recorded in the manager logs from the appearance of the first screen to successful completion of the task, and included the time that participants spent making errors. Although there were outliers, the median completion times were less than 3 minutes for all tasks. Keeping in mind that all participants were completely new to bypass and were completing all tasks for the very first time, these results are encouraging. Variance was relatively low for most tasks, particularly account migration and login, which we think would form the majority of the user's tasks when setting up the manager for the first time. Also noteworthy is that when creating accounts in bypass, 95% of participants used the auto-generated password. As a measure of effectiveness, we examined the frequency and type of errors that participants made while using bypass. Errors were defined as behavior that was obviously unintended, such as a password mismatch or an unfilled field. Some errors may have been excluded in this process. For example, repeated regeneration of a password was not counted as an error, although it was not the intended behavior. Errors were logged by the bypass software and grouped thematically by us. Most participants did not make any errors. The median number of errors per participant was 0, and the maximum was 4. On the left, the frequency of error by study task is shown. Interestingly, participants made the most errors in the bypass account registration task, which was the same as for any password manager. The majority of these errors were to do with picking master passwords that did not comply with the password policy. Encouragingly, there were few errors in the tasks that actually involved using bypass, account login, deletion, and password changes. On the right are errors by type. Password mismatches were the most frequently seen error, followed by entry of an incorrect password, which took place when creating an account on a third-party website. We included 12 Likert scale questions in the post-test questionnaire, asking about the ease of use, perceived security, and desire to use bypass in future. Participants were generally positive about the usability and security of bypass, but expressed reservations about trusting bypass with their passwords, and gave mixed responses about the bypass features that related to user control, such as password auto-generation and automated password changes. Notably, 31% of participants said that they would have liked to have used their own password instead of one generated for them. The results of our usability evaluation suggest that users are able to understand and use bypass's features. Most users did not encounter major problems, and the majority of problems that they did encounter related to the tasks that were not bypass specific. However, a few users did encounter significant problems, and following our evaluations, we had a few general observations about issues that arise when rethinking password management in this way. Bypass adds a layer of abstraction between the user and the website, where all account management-related interactions take place within the password manager. This creates a few design questions. Where should the manager be located in the screen? How should it effectively interrupt users and guide them toward completing tasks in the manager, especially in the learning process? What kind of language should the manager use to help users understand what password tasks they are completing? Our other observation was that Bypass re-architects the password manager to adjust the locus of control for the user. The user is given more control over some aspects of their password management tasks, password changes and account deletion, but less control over the passwords themselves. Users express frustration with this perceived loss of control, and although there's no functional need in a system like Bypass for them to know their passwords, they still wanted to. This might ease when Bypass is used in real life, but it certainly creates a frustrating tension between usability and security. Our other general observation in this work is that testing a password manager is very difficult. Although we did our best to model real-life scenarios in our study, our evaluations lacked ecological validity. In future, we plan to conduct a more true-to-life evaluation of Bypass, but the challenges in doing so are significant and common to other evaluations of password managers. To be used in a field study, a password manager must securely protect users' credentials and information, and the evaluation must also somehow not infringe on users' privacy about the websites they visited and the activities they conduct online. In conclusion, Bypass does appear to improve the usability of password managers in ways that we think offer great promise. Bypass also raises interesting questions about how security controls can be best placed to support end users. That said, there's still work to be done. We plan to integrate new features such as password sharing into future versions of Bypass, and also to more fully explore issues that were left out of scope in this work, portability to multiple devices, and the feasibility for web developers of including the API. Thank you very much for listening to our presentation, and if you have questions, we hope that you'll reach out to us. We're available at the email addresses listed below.
Hi, my name is Drew Davidson from the University of Kansas. I'm going to be presenting joint work with Niels Hansen, also of the University of Kansas, and Lorenzo DiCarli from Worcester Polytechnic Institute. This work is called Assessing Adaptive Attacks Against Trained JavaScript Classifiers. The one-slide synopsis of this work is that JavaScript classifiers need to account for adaptive adversaries. We show this and make this task easier by parameterizing adversary strength by knowledge of the target website and what defenses are being deployed on that target website. We also develop 3 different threat models that correspond to different adversary strengths and show representative attacks in these models. We also use them to characterize the adversary's various capabilities. In order to put this into context, let's discuss what the role of JavaScript classifiers are, and then we'll describe why adaptive adversaries are effective against them. To show our attacks, we're going to use a very classic setup of a JavaScript injection attack. This is kind of a 3-component attack with an attacker, a target website, and a victim user. The attack begins when the attacker crafts a malicious payload, some type of JavaScript, and injects it into the target website via some kind of vulnerability, perhaps a cross-site scripting attack. At some later point, the user will attempt to access the website, and the website will respond with web content, which will include likely static content, some benign scripts which are supposed to be served, and of course the malicious payload which was injected. All of this data is part of the response to the user. The data will be executed in the context of the browser, which unfortunately includes execution of the attack script, at which point the attack launches. This may include some type of damage such as an exfiltration back to the attacker's domain. A great deal of work has focused on trying to prevent the injection in the first place, but it has been found to be very difficult to prevent the injection. In fact, the injection attack remains the #1 threat on the OWASP top 10 list. An alternative, which has been considered and is the focus of this work, is the use of a classifier deployed on the target site. Any script, before it is served to the user, first passes through classification. If the intention is that benign scripts will pass classification and attack scripts will fail classification. Scripts that fail classification are then disallowed from executing, which will prevent exfiltration and effectively thwart the attack. This is a high-level description of what a classifier is, but our intention is to generally consider the behavior of a large class of classifiers. We formalize the problem of classification as a function f from JavaScript program p to one of 2 labels, either b for benign or m for malicious, the malicious obviously being disallowed. In our work, we focus on classifiers which are trained offline on a subset of benign programs and potentially a subset of malicious examples based on the type of classifier. The reason we use subsets here is because it is much more realistic for how real-world classifiers have to operate. In practice, it is infeasible or impossible to have all of the benign scripts as part of your training set. The reason why is because the set of training scripts or the set of scripts may be dynamic and thereby impossible to gather or just too large. So these sets, the benign and malicious, are fed into a classifier which builds some kind of model, and that model is then used for online classification to tell if a script under test is benign or not. Looking at the classifier in a little bit more detail, let's look at some of the challenges involved. The biggest the biggest challenge in the classification problem is maintaining a low false evasion rate. That is to say, it should be rare for a malicious script to be marked as benign, while also maintaining a low false alarm rate. That is to say, it should be rare that a benign script is marked as malicious. Doing this with only a subset of scripts requires a suitable abstraction for how scripts are supposed to be viewed internally by the system. A common solution is to use the abstract syntax tree, a tree-like structure of the script. So the way a classifier often works is the AST is first extracted, and then because the AST is correlated with the program's functionality, so it's a fairly reasonable choice, and then classification is performed on the AST. Of course, this fact that the AST is only correlated with the program's functionality gives an opportunity for adversarial behavior. Indeed, the intuition behind an adaptive adversary is that they might be able to create what's known as a mimicry script in our terminology. That is to say, it looks like a benign script, but it behaves like an attack script. It still fulfills the attack functionality. So it's sort of a wolf in sheep's clothing, if you will. More formally, the way an adaptive adversary works is given a classifier and a malicious program, PM, such that PM is classified as malicious, the adversary seeks to create a new program, PM star, that is classified as benign but maintains the malicious functionality. In order to test whether our adaptive adversaries are effective, we consider two main different types of classification techniques. The first is that of a structural classifier, and to make this more concrete, we focus particularly on a defense framework called CSP Autogen. Although CSP Autogen is a large system, it does have to solve the classification problem, and hence we consider it a good representation of structural classifiers. The way structural classifiers work is that they determine whether a script is benign based on whether it is a structural match for something that it's seen as benign during its training phase. As such, CSP Autogen only needs a set of benign scripts and considers anything that is not similar in structure to a benign script to be malicious. The second type of classifier is feature-based. We use as our representative example a system called JAST, which extracts n-gram feature vectors from ASTs during training and uses both a benign and malicious training set, and then separates them using a random forest classifier. The first threat model that we describe in the paper is the non-adaptive adversary, which has no additional knowledge about the target website. Both JAST and CSP Autogen implicitly use the non-adaptive adversary in their evaluation and are quite effective against it. They have nearly a 0% evasion rate, so hardly any malicious scripts are marked as benign. Our next threat model that we articulate in the paper, we call the reconnaissance adversary. The difference between the reconnaissance adversary and the non-adaptive adversary is that the reconnaissance adversary has a reconnaissance phase where they can collect a set of benign scripts. They can then, instead of injecting the attack script, craft their mimicry script out of the benign scripts that they collect and the attack scripts that are their goal to inject. They then inject the mimicry script, which is then ultimately going to be passed to the user. And if the mimicry is successful, it will pass classification and re-enable the attack. We believe that the reconnaissance adversary is easily achieved in practice because the set of benign scripts can simply be collected by visiting the target website. Clearly, it is the case that those scripts will pass classification and serve as positive examples of benign scripts because they run when the adversary just collects and runs scripts on the site before launching the attack. We introduced two different attacks in the reconnaissance adversary threat model, script stitching and subtree editing. The script stitching attack is quite simple and relies on the intuition that the malicious script is comparatively small compared to a benign script. The attack proceeds by simply taking a random benign script, which was collected during reconnaissance, and appending it to the malicious script. The intuition is that the features of the benign script are expected to drown out or kind of overwhelm the details of the malicious script, and thus cause classification, especially classification which is feature vector based, to ignore the malicious perturbation. The second attack that we develop, we call subtree editing, and this is designed to defeat a structural classifier. It works by looking through the set of benign scripts to find one which is close to the AST of the attack script. So if we have an attack script like this, and we have a training set, which includes, of course, the benign samples and the malicious scripts that we're interested in injecting, we find a script, and if we can find an area of the tree which is close, according to a subtree editing metric that we describe in the paper, we replace that section of the benign script with the malicious one, causing the malicious script to appear structurally, causing the mimicry script to appear structurally similar to the benign script that is effectively hosting it. We now turn to our third threat model, the classifier-aware adversary. This threat model is more powerful, strictly, than the reconnaissance adversary. It has reconnaissance, but additionally has access to details of the classifier and can use that in its mimicry attack. The classifier-aware adversary is also achievable in practice because perhaps the adversary has some sort of inside information about the target website, but if not, they can simply build a surrogate classifier by feeding their reconnaissance scripts and their attack scripts into a local classifier. This enables an additional attack, which we call gadget composition. Gadget composition really builds upon the idea of script stitching, but is slightly more elegant and slightly higher overhead as well. The idea is that instead of appending a random script to the end of the malicious script, you will take small snippets of scripts and find one that, according to the classifier, which you have access to, moves the mimicry script closer to the idealized feature vector in the learned model. So this appending of little script snippets continues for either until a certain number of maximum iterations is reached, or until additional concatenations of script snippets don't result in any sort of improvement. So I'm going to turn now to evaluation of our three attacks. I'm going to limit our evaluation to just some highlights because we don't have really time for the full thing. The main sort of takeaway is that our attacks did end up being quite effective. Against CSP AutoGen, we expected the subtree editing attack would be most effective, and indeed it was. We found that about 27% of domains could have at least one evasive attack get through the classifier, and there was at least one domain with over 700 attacks that could be generated. We found at least one domain in the attack against JAS to have far more than that, almost over 16,000 examples, and overall, because we felt all of the attacks could potentially work against JAST, we tried them all and got almost 100% evasive attacks. Well, 96% of evasive attacks. 96% of domains had an evasive attack work. Although we believe that our results show that neither type of classifier should be considered safe in practice, we did find that the structural classifier did work a little bit better than JAST. We were also interested in knowing whether the characterization of knowledge as being more power for the adversary was appropriate. So we did a sample with 50 domains and considered 34 attack scripts. We found that the more knowledge the adversary had, it actually did enable more attacks. In fact, there were 45 combinations of scripts and domains where the gadget composition attack succeeded, sort of knowing more about the classifier than the simple script stitching attack, which was a reconnaissance adversary example. We were also interested in knowing, given these extra mimicry scripts, could those actually be used to enhance the classifier? In other words, during training of the classifier, could you generate mimicry scripts and use them to have more robustness against these types of attacks? Unfortunately, we found that not to be the case. Adding mimicry scripts to the training did slightly improve the evasion rate, but at the cost of a massive increase in the false alarm rate, all the way up to 12%, which seems to be kind of a deal breaker for a production system. And we feel that this indicates that more sophisticated classification might be necessary rather than just better training data. Indeed, false alarms seem to be a pretty big problem for structural classifiers as well. We did a tenfold cross-validation test with CSP AutoGen and showed that it had an over 10% false alarm rate, which is probably too high for any kind of real production use. So the summary of our evaluation is that adaptive adversaries do increase evasion rate of attacks, and attempts to address it directly seems to incur unacceptably high false alarm rates. We are not the first to consider mimicry attacks against web classifiers. Fast et al. In CCS 2019 created hide no seek, which consists of a single attack, which is similar to our subtree editing attack. It is perhaps a little bit more elaborate. It has a higher evasion rate, but it is significantly higher overhead than the attacks that we describe here. There's also other defense work. Zazzle and Revolver both use ASTs for other types of classification, and we would potentially be interested in seeing if our work applies there. So in conclusion, we believe that adaptive adversaries can subvert assumptions of classifiers and that their knowledge makes them more powerful. We believe that these findings show that a call to arms is necessary for new defenses against AST-based classification as a defense against script injection. And we believe that any further evaluation of those systems should consider the use of our threat model to determine effectiveness. We also believe that there are other attacks under the reconnaissance adversary and classifier-aware threat models, and we look forward to evaluating in those spaces and looking for more attacks. Thank you for your attention. Here's our email addresses. Please feel free to let us know if you have any questions.
Hello everyone, my name is Xiaoyong Yuan. I'm an assistant professor from Michigan Technological University. Today I will be presenting our paper titled Connecting Web Event Forecasting with Anomaly Detection, a case study on enterprise web applications using self-supervised neural networks. This is a joint work with Lei Ding, Malik Ben Salem, Xiaoling Li, and Dapeng Wu. Today I will first talk about the motivation about this paper, and then I will describe the workflow of deep events, which is a novel deep neural network-based approach proposed in the paper for web event forecasting and anomaly detection. And then we will describe the details about the context-based modeling, and then we will talk about the evaluation part of this work. Recently, web event forecasting based on user behavior provides better recommendation, caching, prefetching, load balancing for web applications. However, with the increasing complexity and the functionality of web applications, actually forecasting web events becomes much harder. Browsing a web page can produce a sequence of web events, and the length of the sequence varies a lot for different web pages. A web event can be made for the HTML of the web page itself, but its subsequent events are made for each image, plugin, audio clip, and other contents references in the HTML. The web events for each kind of content increases the complexity of the sequence. The format and the semantics of web events vary significantly from application to application. For example, we show an example of web events in a WordPress website. The user only takes two actions, log in and browse homepage. But these two actions actually generate 33 HTTP requests or 33 web events. On the other side, enterprise web applications provide extended connectivities to an organization's assets and increase the attack surface. These enterprise web applications have become favorite targets of cyber attacks due to the easy access and constantly increasing vulnerabilities. Web anomaly detection, therefore, becomes a critical component to protect web applications against cyber threats. Supervised learning-based anomaly detection solutions build detection systems by discovering abnormal behavior patterns with the use of labeled training data. However, the most existing web anomaly detection approaches are limited due to two reasons. First, high-quality annotated data is not easy to obtain, given the velocity, volume, and the real-time nature of web events. Second, the labeled data is always imbalanced. We can have a much larger amount of normal web traffic data than the abnormal traffic data. In addition, constantly evolving attacks always make the abnormal data irrelevant. To address these challenges, we propose a novel deep neural network-based approach, Deep Event. By connecting web event forecasting with web anomaly detection, Deep Event improves the performance of web event forecasting for complicated web events, and also detects the anomaly by identifying the most unlikely events in the sequence. In this paper, we make the following contributions. First, we propose context-based web event analysis for better user behavior forecasting. Deep events characterizes not only the individual web events, but also the relationships among the web events that co-occur within a context based on user behavior and the web application characteristics. Second, we use self-supervised learning to overcome the need for labeled data. By connecting web event forecasting and anomaly detection, we can formulate anomaly detection as a self-supervised learning problem, which does not require any prior knowledge of anomalous web events and their sequential relationships, but leverage naturally existing evidence as labeled data for training. Third, we propose quantitative measures of the anomaly. Traditional anomaly detection methods usually formulate the problem as a binary prediction task. Deep events actually goes beyond the binary prediction and can measure the deviation of the abnormal event with respect to expected normal events. Let's look at the details. We will start with the workflow of deep event. There are three main components in deep event. First is the event extractor, which will extract web events from HTTP requests. So in the web event extractor, we will first extract content, such as HTTP methods, URI paths, and a number of URI parameters from HTTP requests. Then we will uniform the URI path by removing some random events in the path using two-character Markov chain model. And last, we will identify some rare events which occurs less than a certain times. In this way, we can learn the information of rare or even unseen events during training, which will help us to understand if such rare events in the sequence are anomalous or not. The second component in deep event is called context-based modeling. Given a sequence of web events, context-based modeling will provide the prediction or forecasting for the next upcoming event. We will use event embedding, sequence embedding, and neural networks in the context-based modeling. We will describe the details later. The last component in deep event is anomaly detection. Here we use the results from event forecasting to provide the anomaly score evaluation. We define the anomaly score as 1 minus 1 over tau plus 1, where tau denotes the rank of the newly received request based on its likelihood to appear, which is actually calculated by the context-based modeling for event forecasting. So higher anomaly score indicates the higher confidence level in classifying the events as an anomaly. So in this way, we can connect the web event forecasting with anomaly detection. Next, we describe the detailed approach for context-based modeling. Here we adopt three different types of neural networks for web anomaly detection and for web event forecasting. Here we use three different kinds of deep neural networks: self-attention-based modeling, bi-LSTM-based modeling, and LSTM attention-based modeling. For the self-attention-based modeling, in the training phase, we will input the contextual events and also the events we want to predict or the event of interest into the model. And in the testing phase, we will only input the contextual event and ask the model to predict the event of interest. So after we input these events into model, we will first extract the semantic information and the position information using the event embedding and the sequence embedding in our embedding layer. After generating the embedding on the events and their position, we sum up these two sequences as an embedded sequence and feed them to the next layer, self-attention encoding layer. Self-attention-based neural networks such as BERT, GPT-2, GPT-3 have outperformed the recurrent neural network in almost all the natural language processing tasks and achieved state-of-the-art performance. The attention mechanism was born to help memorize the long source sequences. Therefore, here we use self-attention neural network to memorize the relationship between the web events. In the end, the self-attention neural network will provide the prediction of the event of interest, Yn here. Due to the time limit, we will not go through the details of bi-LSTM-based modeling and LSTM attention-based modeling, but you are very welcome to read our paper for the details. In the evaluation part, we want to answer the following 4 questions. First, what is deep events performance in web events forecast compared with the existing methods? Second, how effective is deep event in evaluating real-world threats? Third, we propose 3 different kinds of deep neural network-based approach. So how do these different neural networks perform in deep event? And last, how do different model settings such as pre-training, window size affect the prediction performance? We evaluate our proposed deep event on 6 real-world enterprise web applications. We collect 84 days of HTTP requests from the 6 applications in an enterprise network. In the left figure, we show the number of events and the number of unique events we collect in the applications. We separate the dataset based on the date and use the first 64 days of data for training and 10 days for validation and the last 10 days for testing. In the right figure, we show the statistics of each training, testing, and validation dataset. We first show the performance on web event forecast. We use Markov model and the 3-gram model as our baseline model for web event forecast. And then we compare the performance of our proposed deep event model with these 2 baseline models. And we observed that our proposed deep event can achieve much higher accuracy in forecasting web events. Next, we show the performance of deep events on anomaly detection. Here we investigate 3 different kinds of web anomalies. First, we investigate 5 real-world exploits on a DevOps web application, Jenkins. Then we evaluate 5 widely used web attacks using SAP, such as SQL injection, cross-site scraping, buffer overflow, CIF injection, and server-side include injection. Also, we randomly generalize some web requests and inject them into the normal request. We want to demonstrate the capability of deep events in distinguishing the normal web requests from the different kinds of web anomaly requests. And we observed that the anomalous requests always have a much higher anomaly score compared to the normal requests, which shows the high performance of our proposed deep event. Next, we compare the performance of different model settings. First of all, we find out that the self-attention-based modeling achieves better performance compared to LSTM attention-based modeling and bi-LSTM-based modeling. Then we investigated the impact of window size, and we found out that in general, longer sequence always performs better in web event forecasting and web anomaly detection. We also observed that the pre-training can always help model prediction in both tasks. In the previous experiments, we always predict the last event in a sequence of web events. However, for many web applications, the web requests are always generated concurrently by a single action. So the concurrent requests make it possible for us to leverage the contextual information or contextual events following the event of interest or event we want to predict. And in our experiment, we find out that predicting the centered events actually improves the model performance. By concluding this work, we propose a self-supervised neural network-based approach, deep event, for web event forecasting and anomaly detection. We evaluate deep event on web requests collected from real-world enterprise web applications and real-world anomalies. By connecting web event forecasting with anomaly detection, deep events outperform the baseline methods and improve the performance of web event forecasting for complicated web events. We also demonstrate the capability of deep event in distinguishing normal web events from different types of anomaly events and measuring their anomaly scores. Thank you for your listening.
Hello everyone, here's a presentation of paper pyDNetTopic, a framework for uncovering what Darknet market users talking about. With the rapid development of internet-based applications, Darknet markets, which are online marketplaces hosted on anonymity networks and are not indexed by any search engine, has become great hotbeds for illicit transactions. Darknet markets provide escrow services for illegal goods such as drugs, weapons, and so on. Formal researches mostly focus on the services, products, or traders in markets, or the functionality and the mechanism of markets, from both technical and legal perspectives. But few pay attention to the forums related with markets. In fact, the collecting, mining, and analyzing of forum data can reveal valuable information about corresponding Darknet market, as well as its users. Researchers can have a quick understanding about the transaction types or goods on sales by finding users in forums talks about drugs, cocaine, or Bitcoin manual frequently. Also, researchers can extract some security crucial intelligence from discussion between forum users. According to the value of information hidden in forum data and the lack of relevant researches, we propose to use topic modeling for data mining and topic extraction. Given a large, unstructured collection of documents, topic modeling is an unsupervised machine learning algorithm that estimates the main topics of discussion. As far as we know, formal researchers simply use LDA for topic modeling, and the topical items have poor interpretability and coherence. The purpose of this work is to present an effective topic model for Darknet market users, as well as an automatic general framework for information mining in Darknet market forums. Our contributions are listed here. First, we propose FBTM, a modified bi-term topic model applicable in large datasets consist of documents with various lengths. FBTM not only handles the sparsity problem when facing short text, but also reduces computational and memory consumption for large corpora, which makes it appropriate for Darknet environment. Second, we proposed pyDNetTopic, a Python-based automatic data extraction and topic modeling framework for Darknet market forums. The functionality of pyDNetTopic is identifying and extracting textual content from files scraped by a web crawler, as well as hot topic detection in Darknet. pyDNetTopic aims to provide a general framework for data mining and intelligence extraction for security researchers quickly understanding underground communities. Third, we utilize pyDNetTopic to reveal the latent topics with representative terms from Agora market-related forums. Items of interest including the state of Darknet markets as well as the security concern of Darknet users provide insight to Darknet or security researchers. Here we introduce some topic models used in our works. Figure A illustrates how LDA models the generation process of a word omega subscript dn in document D within capital N words corpus composed of capital D documents and capital K topics. A. Draw word mixing distribution phi subscript D from Dirichlet prior distribution for each topic K. B. For each document D in capital D. First, draw topic mixing distribution theta subscript D from Dirichlet prior distribution. Then generate a topic assignment Z subscript Dn from document topic distribution multinomial theta subscript D. Finally, generate a word omega subscript Dn from topic word distribution multinomial phi subscript D Z subscript Dn. The reliance on word co-occurrency patterns within documents makes LDA model extremely sensitive to the length of documents. When facing short text, LDA model suffers from severe sparsity problem. To handle this, biterm topic model utilizes a biterm, a single word co-occurrency pair in a single document rather than a single word. BTM models topic distribution over the whole biterms collections instead of deriving it from Dirichlet prior distribution in each document by LDA. DMM model introduces Gibbs sampling algorithm into Dirichlet multinomial mixture model to probabilistically estimate the mixture component and the probability of topic word distribution based on two assumptions. A. Each document is generated by a mixture model. B. Each document originates from only one topic. This assumption, especially the second assumption, can indirectly enrich the word co-occurrency pattern in document level, which makes it suitable for short text. Formal researches focus on the sparsity problem topic models confront in short text and the solution to it, but in Darknet market forums, situation seems more complex. The post corpus in Darknet market forums cannot be regarded as short or long simply. Unlike typical short text collections, such as Twist 2011 or Track, whose average document lengths are 5.21 and 4.94 respectively, the average document length of Darknet market forums are longer than 20 words typically. Although on average, Darknet market forums data seems to fall into the category of long text. However, the forum contains a large number of very short posts, while some overwhelmingly long posts increase the average length of the entire dataset. So simply using LDA may receive unsatisfying results. From this point of view, BTM seems to be an appropriate choice, which produces quite great performance in both short text and long text. However, when performing BTM, another severe problem emerges. As you can see in this table, BTM extracts biterms from corpus to obtain global word co-occurrence patterns. But with the document length L hat and number capital D increasing, the number of biterms increases in square law, which incurs unaffordable memory usage and time consumption. Since the inefficiency of BTM attributes to the redundancy of biterms, an intuitive solution is discarding less indicative biterms. Similar work has been done by Xia to discriminate topical terms using document ratio df omega, which is calculated as m subscript omega divided by capital M. Xia pointed out that the term belongs to general terms when its document ratio is larger than capital M divided by the maximum number of documents a single topic contains. Besides, a term appears only in single documents belongs to document-specific terms, while remaining terms are topical terms. Xia's approach seems to have a good performance in headline-based social news clustering, but it cannot be adopted in darknet market forums situations. The major drawback lies in the threshold for defining general terms. In darknet market forum corpus, it is impossible that we have a prior knowledge of the approximate number of documents the largest topic contains. The unsupervised situation in darknet market forums makes Xia's approach impractical. Inspired by that, we propose filtered BTM to select useful byte terms for topic extraction without any prior knowledge or assumptions. In FBTM, we propose a novel metric named generality gamma omega, which is formulated here. F omega measures the occurrence frequency of term omega in perspective of whole corpus, whereas df omega reflects the document level distribution range of term omega. So gamma omega reflects how centrally the term omega distributes in documents. We believe there is a positive correlation between gamma omega and the degree of how topical term omega is. The detail of FBTM algorithm is shown in algorithm 1. After the calculation of generality gamma omega, FBTM sorts each term in the whole corpus according to its gamma omega and only retains the byte terms consist of terms whose gamma omega is in top eta, which is filtering coefficient specified by researchers determine how many terms in corpus are retained. The rest byte terms are considered as meaningful for topic modeling. Experimental results indicate that by excluding trivial byte terms, extracted topical terms better capture the informative intelligence from darknet corpus. Then we will introduce the architecture of the framework we proposed. Figure is the overview of a framework of pyDNetTopic. The purpose we present pyDNetTopic is extracting the textual content from HTML file obtained by web crawler and uncovering interesting topics with representative words. Based on previous works, we integrate LDA DMM with FBTM, which presented in this paper in pyDNetTopic. Based on our observation of dataset scraped from Darknet, data extraction module utilizes a strategy that choosing files with topic in their names and selecting the inner elements to get textual content of posts. Then pyDNetTopic performs a pipelined pre-processing procedure to the raw blocks of content to transform them into appropriate form for topic model. Such procedure is concluded by our series of experiments combined with related works. During the experiments, we find that a mass of post topics center in drugs, which contains a lot pure numbers, indicating the weights or prices of drugs. Addition to numbers, such posts always contain a lot of ill-formed words with only one character. Another phenomenon we find is that there are many quite long meaningless words, stemming from the URL or PGP public keys in generated corpus. These words appearing in the extracted topics will make the output confusing. pyDNetTopic removes these meaningless words out of consideration for efficiency and performance. When we just use the standard stop words list, we find the results of topic model output revolved around curse and common words. To alleviate this, we perform FBTM repeatedly on our generated corpus and choose the top 20 most relevant words within each topic as representative word set. When we find words that add no insights to the potential topics in typical word set, we remove such words from raw corpus by adding them to the stop word list. We repeat this operation until in the top 20 typical word set there are no obviously meaningless words. We conclude our final results of stop words list in an appendix. We believe this stop words list can be directly applied in future related researches. Here, with different modes, pyDNetTopic provides different text extraction strategies. In long text mode, pyDNetTopic aggregates every single response within a post into one document. In short text mode, pyDNetTopic writes every single response into one document. Aforementioned two modes correspond with different applicable conditions of topic models. LDA model is fit to long text, while FBTM and DMM is suitable for short text. In pyDNetTopic, we choose the relevance of each term rather than its topic word probability to rank the top topical words list of each topic. The definition of relevance makes a trade-off between the topical word probability with its corresponding lift, which is calculated by the topic word probability with its marginal probability. By introducing the lift term, relevance decreases the rankings of globally frequent terms. On the other hand, the topic word probability term balances the noise introduced by lift term. In order to perform a quantifying analysis, we choose a series of automatic and unsupervised evaluation metrics. Coherence scores for topic quality evaluation. Coherence measures do not rely on any human annotators or extrinsic reference collections. The insight of coherence is based on the observation of human expert annotations that pairs of words belong to the same topic clustered by the model tend to co-occur in the same document, while word pairs belong to different topics have little co-occurrency tendency. We choose UMass coherence, UCI coherence, and centroid coherence for topic quality evaluation. The detailed calculation can be seen in our paper. In order to make a comprehensive comparison of the clustered topic quality between three topic models, LDA, FBTM, and DMM, we choose Agora Forum dataset in the Darknet market archives. For time limitation, we randomly choose 1,000 files from a part of subfolders, which span a whole year in 2014, for topic models in pyDNetTopic, respectively, and calculate the evaluation metrics. The UMass, UCI, and centroid coherence of three topic models in different dates of Agora Forum dataset is shown in these figures, respectively. FBTM achieves almost 150% and 250% higher UMass measures than LDA and DMM. UCI coherence gives a similar results. Due to our observation of training files, we attribute the dramatic drop of performance of LDA in May 24 to the higher proportion of short text in dataset, especially some overly short documents. The severe negative affection on performance demonstrates the sparsity problem of LDA. On the contrary, the stable measures of FBTM demonstrates its capability of handling various length files. About centroid coherence, situation seems a little different. The coherence scores of DMM are slightly lower than FBTM, while LDA still performs worst. Table 3 lists some typical topics with their related words selected by three topic models in February 3rd. We can see that FBTM can capture the typical terms of researchers' interests better than DMM and the LDA. According to comparison, the topics FBTM generates consist of more specific words. The word cache, SDB, and sativa, which are kinds of drugs, and the keyword DDoS, Bitcoin fork, are selected only by FBTM. According to that, we can have a quick understanding about the majority drugs Darknet users prefer. The Bitcoin mixing up platform prevalent in Darknet, as well as the concern against DDoS attack or business fraud from Darknet users. The topics LDA generated is much more ambiguous with a high repetition rate of topical words. Only thing we can see is topic 2 related to the trust issues in Darknet market due to some words like scammer. In general, we can conclude that FBTM can provide a more specific informative intelligence from Darknet, which makes it a better choice than LDA than used mostly in previous works. Here we give an analysis of topical results listed in detail in appendix to show how topic model can help Darknet intelligence mining. Results in appendix supported the role of Agora Market serving as a social platform that enabled users to exchange their goods or reviews for promoting underground transactions. Similar to traditional underground forums, many vendors tend to publish advertisements of their products with the introductions and attached links in the forums, especially new coming vendors. This can be reflected by the topic with the keywords such as welcome paired with the vendors' names. The topic words reveal some active vendors such as Markovich, Trim, SQK. An important functionality of underground Agora forums is it builds a reputation system as a complement to the market. Forums provide a platform for exchanging evaluation experience in transaction or drugs with freedom. The common topical words smell, feedback, quality come from posts buyers exchange their usage experience or recommendation on their selling drugs. Prevalence of scammer or trust reflects the fraudulent conduct in the darknet market forums. FBTM also lists some prevalent goods, which are not captured by other models. Another interesting findings are the transaction means used by darknet users. The common choice for goods delivery is USPS owing to its high occurrence rate in topics around transaction or delivery. Cryptocurrency is another big issue discussed frequently in darknet forums. Security concern is always a significant issue in darknet forums. Therein, anonymity is the most frequently discussed property due to the appearance of terms anonymous or stealth. We find the most prevalent tool darknet users used for confidential communication is PGP, Pretty Good Privacy, which is implemented by a free open source software, GNU-PG. Another important communication service mentioned in the forums are emailing, indicated by words such as Tor mail, Vmail, URSS mail, Thunderbird, and SMTP. Besides, darknet users also use Pigeon for instant messaging. As for anonymity of transaction, Bitcoin Fog is the most prevalent coin join platform appearing in the topic about security. To prevent business fraud, darknet users take measures which can be seen from the terms such as escrow and multi-sig, which aims to prevent markets scamming users into purchasing items that they will never receive. FE, which is a transaction form meaning finalized early, where the buyer has to release the fund kept in the marketplace wallet to the vendor before the goods were actually shipped, becomes prevalent since February 24 to protect vendors. We believe the results analysis mentioned before can demonstrate our works to the intelligence mining of darknet market. Thanks for your time.
Hi, I'm Fatema Rezai. I want to talk about Bitcoin Hunter. This is a joint fork from University of Massachusetts Amherst and Technion. In this paper, we differentiate Bitcoin traffic from others because of the adoption of Bitcoin and similar cryptocurrencies in industry. It is important for consumers and industry to have reliable access to their Bitcoin assets. We want to see how easy it would be for a government or ISP to detect Bitcoin traffic and block it. For example, what's going to happen if Great Firewall of China decides to block all the Bitcoin traffic overnight. In this paper, we look into Bitcoin traffic and characterize it. We design classifiers based on the characteristics of Bitcoin and try to identify Bitcoin in presence of background traffic. We run experiments on the Bitcoin over Tor and its pluggable transport. First, we look into the different messages that are generated by Bitcoin peers. We look into the distribution of the packet sizes in different messages. And also we look into the histogram of the packet size in the aggregate traffic. We collect more than 1 month of Bitcoin traffic and look into the different messages that are generated. We find out that the majority of the messages are very small and the dominating messages are inventory and transaction. These two figures are showing the packet size histogram of these two messages. As you see, most of the packet sizes are very small, which actually makes the Bitcoin very distinguishable from other traffic because of these small messages in these dominating small messages. The second thing that we look into is the shape of the Bitcoin traffic. Bitcoin traffic works in two different modes, relay mode. First one is full relay mode. In the full relay mode, the whole block that is generated becomes transmitted between the peers, which actually gives spikes of 1 megabyte every 10 minutes and steady traffic on the rest of the times. The second mode is compact relay mode, which was introduced in 2016. To actually reduce the waste of bandwidth in the previous mode. Here, instead of sending whole block between the peers, only a sketch of block is transmitted, and this shows a non-deterministic behavior. The first set of classifiers that we design are size histogram. Size histogram of the Bitcoin is pretty unique when it's compared to other protocols. These three figures are showing Bitcoin, VoIP, and HTTP, and as you see, the packet size histogram is pretty different and it's distinguishable for Bitcoin. The second classifier that we design is size Tor. As you know, Tor pads the messages, pads the packets to make them single cell or multiple cell. Because of the small messages that we have in Bitcoin, those actually gets padded to become single cell packets, and because the majority of the packets are very small, the ratio of messages are small, the ratio of the single cell packets in Bitcoin when it's over Tor is much larger than the regular traffic over Tor. This figure shows the regular traffic over Tor and Bitcoin and the ratio of single cell size packets. And as you see, the blue one has a larger ratio, which is the Bitcoin. The second classifier that the third classifier actually that we have is the shape-based classifier. We see that the overall shape of Bitcoin is unique. since it has spikes in every 10 minutes and steady traffic at the rest of the time. The left figure is for the full mode and the right one is for the compact mode. As you see, in the full mode we have spikes of near to 1 megabyte every 10 minutes and steady traffic at the rest of the times, but these spikes are much larger for the compact mode because we are not sending the whole block between the peers. In the shape-based classifier, what we do is we get the time of the blocks, generation of the blocks from blockchain info, and for each time of block, we look into a window of W before and after the block. And if the difference of the traffic volume is between a range that we, between a certain range, we would say that this block has been detected. And if the ratio of these blocks that are detected are more than a threshold that we have, we would say that this traffic is Bitcoin. The last category of the classifiers that we have is deep learning based ones. To deep learning and machine learning based classifier has been used to classify different traffics. Here we use deep learning to classify Bitcoin. The feature that we use for the to distinguish Bitcoin is the shape of the Bitcoin traffic, for which we use volume over time to capture this shape. So, as I said, our feature is volume per interval. For the interval of time, we have 1 second, 5, 10, and 20. And we see that the 10-second of time interval volume for time interval gives us a better result. The sample size that we have is 10 minutes, which is the smallest size to actually have at least one block. And we have a small fully connected network with 2 hidden layers, and we are using binary cross entropy as the loss function, and the Adam optimizer is used to minimize the loss. The last classifier that we have is the combined classifier, which, as it is shown from the name, is combining all the previous ones. We have the features from size histogram and volume over time, and we are using a larger network to distinguish Bitcoin. And same as before, we have Adam optimizer and we have binary cross entropy as the loss function. So let's move on to the experiments and the data set. So we use Bitcoin traffic. We collect Bitcoin traffic for over a month for full mode and compact mode. We have Bitcoin over Tor and pluggable transports in compact mode, and we have HTTP over Tor and its pluggable transports, and we have Bitcoin with background traffic in full and compact mode. And also we use KDA dataset to have different applications as the background noise for Bitcoin. This table shows the KDA dataset that we have. We use more than 30 hours of KDA dataset, and this is the different traffic classes that in these 30 hours we had. The majority are, as you see, HTTP and DNS, and we have other categories like Telnet, SSH, SMPT. So we have 4 different user profiles to evaluate the strengths of each classifier. According to strengths of each classifier, we use different simple user, simple noisy user, complex web user, or complex KDA user. The simple user is when there is no background traffic on Bitcoin. We want to distinguish Bitcoin from HTTP, since HTTP traffic is the majority dominating traffic in the network. The second user profile is simple noisy user, when we have one open tab on the background. When I say one open tab, it means if we have 10 minutes of traffic, we have 10 minutes of browsing websites on the background. And we have complex web, which means we have up to 5 number of open tab on the background, and complex KDA user, which has up to 5 applications running in the background. So this figure shows the result of size histogram classifier. For the size histogram classifier, we use the simple noisy profile, which means we have one open tab on the background. As you see, when we have 10 minutes of traffic and 30-second think time, we can reach more than 90% true positive and 0 false positive. So the think time is the time that we wait on a website before opening a new one. And as we increase the think times, the noise, the background noise is decreasing. This figure shows the window shape classifier on full mode. So the window shape doesn't work on the compact mode because the because the blocks are smaller in compact mode, and it's easy to distinguish them. As you see, we have three lines here. The black line is showing the Bitcoin traffic using the ground truth, shows the block detection rate for that. And we have the red one, which is the Bitcoin traffic using ground false. So the ground truth is the real time that we get for each block from the blockchain info, and the ground false is the time series that we are synthetically building by trying to mimic the behavior of Bitcoin. So we actually, using these two lines, we have to set the eta, which eta should be chosen to be larger than all of the numbers for the red ones. And if we choose eta here, we see that our traffic, we are actually able to have true positive of 100% and 0 false positive. And the blue one is showing the HTTP traffic using ground truth. So since all of the numbers are smaller than this eta, we cannot detect any HTTP traffic as Bitcoin. Also, since all of the numbers in the black are larger than this eta, we can actually have the true positive of 100%. The last set of the classifiers are deep learning and combined classifier. So using the deep learning one, we have actually all of the user profiles. It means we have Bitcoin with up to 5 number of applications on the background or 5 number of websites on the background. As you see, we can reach more than 90% true positive and 2% of false positive when we have 40,000 training size. And this result improves to more than 99% true positive when we are using the combined classifier and with 0 false positive. To compare the different methods that we had, deep learning is giving us better and more reliable results. The shape-based only works on the full mode and also when there is no background noise. The feature-based, the size histogram, is giving us 90% true positive and 0 false positive when there is 10 minutes of traffic with 30-second think time. And the last category, which is deep learning based and combined, is giving us more than 90% true positive for the first method, deep learning based, with 2% false positive, and when we use combined classifier, we have true positive of 99% and 0 false positive, which is better than all of the previous classifiers. So as a countermeasure, we use the Tor. We want to distinguish Bitcoin traffic when there is background noise and it is tunneled over Tor. Here we are using the user profile of complex web. As you see, having only one open tab with think time of 0, we can reach more than 90% true positive and 0 false positive using the size Tor classifier. Also, we run the deep learning based and combined classifier on Bitcoin over Tor, and we see that we can reach more than 99% true positive and less than 1% false positive with the combined classifier. Here we characterize Bitcoin traffic and study its resilience to blocking by ISP and strong entities like government. We designed classifiers for Bitcoin, and we showed that our classifiers work even when Bitcoin is over Tor, and when there is complex background noise, like up to 5 number of open tabs or up to 5 number of applications running.
Hello everyone, my name is Golam Dastakir Bashar and I am a PhD student at Boise State University in the Department of Computer Science. Today, I am going to present the paper entitled Proof of Q as Consensus Protocol for Private Blockchains using Intel SGX. I hope you will find this topic interesting and informative. Alejandro and Dr. Gavi are also the authors of this paper. Through the presentation, I want to talk about the consensus protocol and I will briefly discuss our work, which is proof of Q, and how we implemented the protocol. I will also talk about the experiments that we have performed, then finally make a comparisons in our work over an existing protocol. Introduction. Consensus protocol are mechanisms that enable a group of entities to reach an agreement of a specific subject. The popular types of consensus protocol are leader-based and traditional Byzantine fault tolerance-based. A consensus protocol in blockchain system is typically required to support three properties. Liveliness means transactions are added to the ledger in a reasonable time. Consistency, this means all parties have the same view, and fairness indicates all nodes are equally likely to mine the next block. Public consensus protocol is open to join without any approval and data visibility is set to public. Generally, this type of consensus protocol offers an economic incentive. Examples of such consensus protocol are proof of work, proof of stake, and delegated proof of stake. In private consensus protocol, participants need prior constants to join. Those are more centralized than public consensus protocol, and the transaction visibility is set to private. That's why it is only available to the participating nodes. There are some examples of private consensus protocols. In private consensus protocol, the level of access, visibility, and execution can be controlled. Due to transaction visibility set to private and only available to the known nodes, a limited numbers of nodes can participate in private consensus protocol. Here, the private consensus protocol are much faster than the public in respect to throughput. However, they are still slow in relation to traditional transactional system. Trusted execution environment is a secure area of a main processor. It guarantees code and data loaded inside to be protected with respect to confidentiality and integrity. Trust Zone from ARM and SGX from Intel are the examples of TEE. Our contribution: in this work, we propose a private consensus protocol based on Intel SGX that achieve fast transaction processing, low energy consumption, fair distribution, easy verification, and avoid high resource utilization. Our goal is to optimize the performance of the network concerning throughput, scalability, and fairness. Our work outperforms POET in terms of throughput. Related work. Nakamoto's Bitcoin, Litecoin, and Ethereum does not use TEE, and Ethereum is shifting to proof of stake due to the energy issue and to have better scalability. Proof of elapsed time was developed by the Intel back in 2016. Due to its access control nature, it is most appropriate for private blockchain where certain works will be executed on TEE by a certain authenticated nodes. It creates an attestation for a piece of code and protects the code from external access. Proof of luck is an example of Intel SGX-based consensus protocol where all participants select a random number and one with the highest number wins. Proof of TEE stake is a variant of proof of stake protocol that allows a use trusted execution environment to enforce honest behavior of the validators. Each consensus protocol is unique based on how it works and how it creates a block. Disclose the evidence. Table shows the comparative evaluation among some of the protocols designed for TEE based or not. This is the comparison of SGX-based system. Background. Intel Software Card Extension allows application to run in a completely isolated area called enclave. Most desktop mobile released after 2015 fall supports SGX. An SGX application can handle 5 to 20 enclaves. So SGX breaks down an application into two segments, enclave and untrusted part. The code in the enclave is used to handle the secret data. Interaction within those two parts happens via call gate, eCall, and OCall. Figure A shows the high-level view of eCall and OCall communication, and Figure B shows the execution of an SGX application and the way SGX safeguards an enclave from outside program. SGX is capable to generate a random number via SGX-read_rand function, and many researchers have already been established that this is random number generated is secure and cannot be modified outside from the enclave. C and C++ only the supported language till now. Remote attestation is an exceptional property of Intel SGX to establish a secure environment between the server and the node. Simply, in computing, the term attestation means a procedure to verify the identity of a software and hardware. By following the remote attestation flow, a client can ensure its identity and its pureness. POET is usually used on private blockchains to determine the leaders of the block on a specific network. After joining a network, each node must ask for a wait time from an enclave and then wait for that assigned time. And the node who finished first, that is the node who is the shortest wait time, will act as a leader. In order to reduce potential collision, waiting times need to be longer, said by Chen et al. In Deng et al., they propose SPOET that in the paper they said if the shortest wait time and the another wait time are conflicted by a fewer, then the propagation delay will be result a still block. And to reduce this still block, Deng et al. In 2019 said we have to restrict the number of nodes, which we call POET plus. Proof of queue. From here, we will frequently use the term quantum time and TR. So quantum time means the amount of time a node will get a chance to execute for a single pass. TR means a relationship engaging level between a set of nodes to assign quantum time. Our protocol consists of two phases, server and client. The initial step is registration. In this phase, nodes need to join the network for authentication. Each participating node generates a random wait time using the enclave called SGX time and waits for it to be expired. After it expires, nodes become the leader. The wait time and the leadership for each node will be approximately same after a certain time. In our protocol, when a node joins the network, it gets a range from the server to generate a random wait time from its enclave. After having their SGX time, the node needs to submit it to the server for further verification. After successful verification, the server adds the node ID to the queue as it arrives. Subsequently, the node determines which tier it belongs and it can calculate the quantum time for that particular tier for the time being, which is equal to the amount of time it can be executed for that pass. If it remains in the waiting part of the queue and any nodes join which belongs to the same tier, then it needs to recalculate the quantum time. A new node can also be added at the end of the queue. While a node is executing and a new node joins that belongs to the same tier, it won't affect the quantum time of that executing node at that moment. However, if a node is unable to finish the SGX time, it must need to recalculate all those credentials. After completion of each node's quantum time, the remaining SGX time of the currently executing node is checked. A function called timeLeft keeps track of the remaining time over SGX time. The figure shows the various states of a node before becoming a leader. The server will always wait for a join request from its node. Whenever it gets a request from its node, it calls register function. If it is valid, it generates an identification number put into the queue and sends an acknowledgement back to the node with its node ID and SGX time. Immediately after receiving the SGX time from node, it calls the verify function. If it does not fit in the range, the SGX time, it will discard the connection. After successful verification of SGX time, the server stores the time when it's submitted, and that will be treated as its arrival time. Then calculate the quantum time according to the TR and obtain the starting time for the particular node. Then the server builds an SGX table based on all available data. All nodes now have the same database concurrently that server has, and almost every data will be replicated to all the nodes, which accelerate the speed of the network. When a new leadership has been claimed, a node is supposed to announce that it has completed its SGX time, so that is considered to be a leader and get appended to the blockchain and dequeued from the queue. Figure shows the top level architecture of proof of queue. So waiting time, the definition is the inactive time of a node after considering its arrival time. Simply the amount of idle time it is spent in the queue before the last pass finishes. And the average waiting time is the average value of the wait time of n nodes and can be calculated by equation 2. And elapsed times, the entire time needed by a node to become a leader. The average elapsed times of a node can be calculated by the equation 4. Node side protocol. When a local SGX connects to the server, it gets a NID and the range of to generate the random SGX time, which is subject to change subsequently after each round. If there is more than one node, then the node ID will play a vital role to get involved into the protocol. If queue is null, then the node ID is added at the front of the queue. If queue is not null but the remaining time of the current execution node is 0, then node ID is added in a FIFO manner. Nodes gets the SGX table from the server that consists of all metadata. Based on all those available information, all particular nodes can calculate which tier it belongs, when it will be its start time. So it is worth mentioning that for a specific tier, whoever comes first, it will start first. If there is no nodes in the overall queue, then the current node may carry on. At any stage, for a particular node, if SGX time or remaining time is less than its quantum time, then its quantum time will be assigned as updated its remaining time. Figure shows the inter-process communication between the nodes and the server. Experimental evaluation. We built a prototype proof of queue in C++ to evaluate this performance. The design of a good consensus protocol must satisfy the following goals: back up a large-scale network, obtain a higher throughput, and achieve fairness. All experiments performed below with the configuration of these systems. Throughput. The purpose of this experiment is to measure and compare the throughput of POQ and POET. We ran multiple experiments with different parameters. We measured the number of leadership per seconds for 10 different nodes and 3 SGX time range, which is 1 to 100, 1 to 500, and 1 to 1000. In the baseline case, we assume that all nodes arrive approximately at the same time. Then we allow them to join randomly at different times when a certain range of arrival time with the same tier, which is 5. We ran each test 50 times so as SGX time and arrival time are generated randomly. The graph with different arrival times deals with the average result of the test, where 20% of nodes leave the network randomly at any time after becoming the leader, at least for once. By comparing POQ and POET, with POET, we observe that throughput of POQ is higher in both cases. All nodes join approximately at the same time or when they join at different times. The difference between the two protocols' throughput could be as low as 0.3 and as high as 3.5. In this section, we evaluate the scalability of our protocol. We start with a network of 2000 nodes, then double the network size 5 times, raising to 10,000 nodes in the last settings. We keep the same parameter involved in the previous figure, but the larger number of the nodes. We ran the experiments only once until the nodes becomes exactly one leader. It should be noted that epoch time is longer seconds in 2000 nodes to 5 for different numbers of nodes. And by observing the graph, we conclude that average waiting time and average elapsed time for different size of network increase linearly as the network size grows. We also measured remote attestation, which takes roughly 2 milliseconds, and we did not consider in our result data. A consensus protocol is fair if a miner with P share of the overall resource ratio can produce a block with a probability P. In this section, we measure the relation between a number of SGX machines a node has and the number of leadership it can reach. We conducted this experiment with the same parameters elaborated in above figure. We ran the experiment 50 times, and the figure reported below are average over 50 independent runs. The graph shows the cumulative average leadership of a miner who has a certain number of SGX per node. The x-axis indicates the total number of SGX a node has, and the y-axis is the average leadership. After running our experiment, we observed that the probability of being chosen to be a leader is scaled linearly in relation to the number of SGX machines. Conclusion. In this work, we proposed proof of queue, a leader-based consensus protocol for private blockchains that utilize Intel SGX to ensure all nodes in the system to honestly run trusted code to become a leader. Proof of queue maintains queues for different tiers, keep tracks of the quantum times executed by all the nodes, and updates the state change to all the nodes. Proof of queue is specifically designed to avoid the collision in leader election than existing proof of elapsed time protocol. Also, our protocol is suitable for a large number of nodes with an enormous wait time. The design of proof of Q shows that it maintains approximately similar wait times and elapsed times for all the nodes. Based on the simulation and large-scale evaluation of proof of Q, we showed that no nodes left behind. Also, our protocol is suitable for a large number of nodes with huge wait time. We evaluate proof of Q against three metrics: throughput, scalability, and fairness. The result shows that proof of Q can offer better performance. Besides, proof of Q scales fairness linearly with the number of SGX machines. Thank you. Any question?
Hello everybody, this is Sang-Yun Cheng from University of Colorado Springs, or UCCS. It's my pleasure to present our work at SecureComm. The work is titled Share Withholding and Blockchain Mining, and I'm the author for this work. So as more of a background, this work is about cryptocurrency. Cryptocurrency processes financial transactions, generate currencies in a permissionless environment without a trusted third party such as a bank. Because it doesn't rely on the trust of such centralized entity such as a bank, the cryptocurrency is designed for censorless and anonymous financial transactions. Examples of cryptocurrency, the two most well-known and the two most popular in market cap are Bitcoin and Ethereum. Blockchain is the underlying technology for cryptocurrency. Blockchain, has a distributed ledger. The distributed ledger is stored across the distributed set of miners, or distributed set of participants. The ledger is comprised of blocks, and each block, or from one block to another, they are dependent or chained with one-way hash functions. A big question for blockchain is, how does everybody agree on the next block? And the block actually includes the transactions as well as the reward, the newly minted coin information. But because we want to have distributed operations, in distributed setting, how do we agree on what the next block should be? To address that question is the distributed consensus protocol. And the most popular consensus protocol, or the popular mechanism for distributed consensus protocol, is based on probabilistic proof of work, or POW. In this case, if it's POW-based consensus protocol, then the participants are called miners. And what the miners do is that they find the input of the hash function, or pre-image of the hash function via brute forcing, and once that actually satisfies a condition or a difficulty condition, then they found a block. And this POW is used in Bitcoin and Ethereum. So the miners in these POW consensus protocol are financially driven. They are financially incentivized to participate in the POW consensus protocol, because once they find a block, when they find a block, they earn the corresponding reward in the forms of new currency or transaction fees. The POW consensus protocol is also designed to be fair in computational power. What that means is if the miners have greater computational power, then they're more likely to find a block and win the corresponding reward. The POW consensus is also random probabilistic, and the winning event is sporadic. And because the winning event happens rarely, because the miners are competing with other miners spread across the globe, miners often join a mining pool. In mining pool, the miners share their computational power as well as the corresponding reward. So if one miner finds a block within the pool, then that reward gets distributed across the mining pool. And the motivation for joining the mining pool is to smooth out the randomness or to reduce the reward variance. And it's very popular. It's very popular to join the mining pool so that the miners have more stable income source or reward when they mine. An important concept within mining pool to this work are the shares. The shares are also called partial proof of work, or PPOW, and these correspond to solving the same block, or trying to find the same block. So it's the same same computation process with the same inputs, but the shares correspond to easier difficulty or lower difficulty. So for every block, there are multiple shares. And mining pool uses shares to provide more samples for estimating who's contributing how much for mining process. And because they have more samples, they have better granularity in terms of estimating who's contributing by how much. So mining pool is very popular, and our work builds on mining pool, and it actually uses this share mechanism for our novel thread. So the consensus protocol is to submit the blocks and shares once they're found. But in the past decade or so, the researchers started questioning if the protocol, if the current POW protocol is incentive compatible. In other words, can there be threats where they diverge from the protocol and get greater reward than have they complied to the protocol? And more specifically, with these threats, they'll actually withhold or control the timing of the block submission. These threats, where they control the block withholding, the block submission timing, the most relevant to this work are the ones based on block withholding or the variations, more advanced variations of block withholding. So some of the literature is the block withholding by Rosenfeld in 2012, fork after withholding, which generalizes block withholding, but it introduces additional logic, which appeared in 2017. And our previous work of Uncle Block Attack in 2019 generalizes FAW even further when the Uncle Block rewards are enabled. So for our threat model, we consider a miner who is rational and uncooperative. By rational, the miner or the attacker miner is financially driven. And by uncooperative, we mean that the miner is willing to diverge or change the protocol. And this is actually because our work is aligned to the incentives of the miners, our work is actually more generally applicable than the malicious threat model. So any miner who's willing to diverge from the protocol and want to increase their profit, they would do so. So it's not just the malicious threat model, but it's closer to the rational model. The threat strategy, they also sabotage or reduce the rewards of the others. So that is close. They also have the security implication where they have destructive impact on the other protocol compliant miners. Okay, so here's the setup for the block withholding and their advanced variations. The attacker has multiple pools, the main pool where the attacker keeps all the reward if it finds the block. So you can think of this as a solo pool versus, it also has or compromise the victim pool. And in the victim pool, the attacker is one of the many members in that pool. So if a block is found within the victim pool, then the attacker shares the reward with other pool members. And the attacker needs to split its power across these pools, cannot double dip. So our setup is the same as this setup, and this setup is the one that is being used for block withholding, fork after withholding, and Uncle Block Attack. The attacker, because of permissionless environment, it can generate many accounts, meaning that Sybil is easy. And so this is and because of the permissionless nature and some of the pools being open and registration, easy registration, because of that, this is a relevant model. Our work actually builds on this model, which has been adopted, by these block withholding literature. And it has the same, attacker setup. However, share withholding actually focus on gaining reward advantage within the pool. And this is in contrast to the other block withholding threats, because the other block withholding threats, focus on the interdynamics across the pool, and the attacker goal is trying to, increase the reward of the main pool, as opposed to, while lowering the victim pool reward. In contrast, share withholding actually focuses on getting more payouts within the mining pool. So it's increasing the payout reward while decreasing the other reward payout, for the other pool members. So it's within the pool. Now, as we'll soon see, the share withholding requires the knowledge about the impending block submission. And because of that, there can be other ways of achieving that. But, to provide a concrete case where that is satisfied, we actually introduce the share withholding threat in conjunction with these block withholding threats. So we consider share withholding with fork after withholding, or share withholding with UBA. Okay, so share withholding, so this, slide shows different threat strategies, which are based on withholding blocks, withholding shares, from left to right, from honest to SWH UBA. Generally speaking, it's in increased complexity. So we're giving the attacker, more sophisticated control, more options, and that's applicable for, FAW, generalizing block withholding, because it's introducing another logic. And it's also applicable for UBA, generalizing FAW as well. So the worst case of UBA being FAW, the worst case of FAW being block withholding. We build on those literature to introduce share withholding. Share withholding withholds the shares, both blocks and non-blocks. So it actually withholds blocks, but it also withholds non-block shares, and submits them right before the block. And we'll soon see that share withholding is relevant in the decaying payout scheme. So we take a formal approach to study share withholding. Our model, we take a staggered approach in introducing our model. The first model is more about the mining game and the interpool dynamics, and we build and adapt the model in the previous literature. We try to be somewhat consistent with the previous literature, and because share withholding introduces greater complexity, we build on top of the mining game and model the mining pool game. And this is a new model to characterize the share submissions and the corresponding payout. So to summarize our theoretical results, we provide a couple of theorems. These two theorems that I'm showing you focus on the scope of share withholding. So theorem 1, attacker has no reward gain to delay its share if the payout scheme has a fixed timeout payout. Fixed payout. So share withholding is relevant, given a decaying payout scheme where the payout of a share depends on, how long it has been since it was submitted. An example of that is slush pull. In theorem 2, given a decaying payout scheme, such as slush pull, attacker has positive reward gain if it has information about when the block will get submitted with a non-zero probability. So if the attacker has some information about the impending block submission, then share withholding attacker, can have a positive reward gain. And these are, paraphrased from what is written in the paper. So we have theorems, to better establish the scope of the share withholding attack. And then, given those, we analyze the payout. So the payout is the intra-pool payout and the reward gain. And the reward gain actually incorporates the payout analysis, because the reward gain actually looks at the reward of the main pool. So it looks at the interpool dynamics as well as the intra-pool payout. This presentation will We'll skip the equations on the reward gain, but please see the paper, for the reward gain analysis. So here I show you two equations. In the capital tau are the intra-pool payouts, or the payout gain. There are two versions of the equation, one on the left and the one on the right. The one on the left is based on iteration. It's more precise. We provide a lower bound on the payout gain, and we use this lower bound for the rest of the analysis. And even if we use the lower bound, we still show that there's reward gain by using share withholding. The expression on the right-hand side is an approximation, and this approximation is easier to analyze. It's simpler, and the behavior captured by this approximated equation on the right equation, we saw that behavior in our simulation analysis as well. So the approximation right equation, according to that, the payout gain increases with the attacker power within the victim pool alpha prime. The payout gain decreases with other pool members' power beta, and the attacker's payout increases with the payout decaying D. The payout decaying D is how quickly the share reward decreases, as it becomes longer, or as it becomes older, as the share submission becomes older. And this is important because this actually motivates share withholding, and to withhold a share up to the point where the block is being submitted. Okay, so we do simulations analysis. And our simulation is based on the real-world implementations. We emulate the real-world implementation. We assume that the attacker chooses the optimal infiltration power. And we, these next couple of slides, we'll look at the attacker reward with respect to the attacker computational power alpha and the C prime. C prime is important because C prime is the fraction or the probability of the payout earned from withheld shares, given another block is detected within the pool. So we actually have a parameter C, which we took from the FAW paper, the fork after withholding paper, and that's actually the fraction of winning the collision or the fork race when there's a fork with a different pool. Now C prime is similar, but it's the fraction of winning that forking race within the pool. So it's competing with another pool member submitting a block. And we see that if C prime is equal to 1, meaning that the attacker always, and this C prime is important because it also impacts the shares that are being withheld as opposed to just the block. If C prime is equal to 1, then share withholding with UBA always outperform UBA. Generally speaking, a lower power attacker chooses share withholding with UBA, while a more power capable attacker chooses UBA. So for example, when C prime is equal to 1/3, then this is the vertical line threshold where if the attacker computational power with respect to the network power, if that's greater than this threshold, then the attacker will choose SWH UBA, whereas if it's greater, then it will choose UBA. And we actually see that this threshold, the changeover point, actually increases, as C prime increases. A couple notes about C prime. C prime is bounded by the stale share reward. So some pools actually implement the stale share reward. And the attacker can, increase the C prime by combining with networking-based threats. One extreme being the Eclipse attack against the pool manager. So to conclude, share withholding attack withholds shares to increase the intra-pool payout, and this is in contrast to the different block withholding threats, which consider the inter-pool dynamics and try to increase the main pool reward with the expense of the victim pool reward. We introduced share withholding in conjunction with UBA and FAW. The paper also includes the Nash equilibrium analysis, so I encourage you to check it out. We study how SWH impact changes depending on the system parameters and attacker capabilities. This is an exciting field. We need more research and development to secure the blockchain. So with that said, thank you very much. Thank you very much for paying attention to this presentation. Hope you enjoy the rest of the conference.
Hello everyone. Here I'm going to talk about our study on underground activities on the e-commerce ecosystem, the Incentivized review group. This work is done with Yubao Zhang when he was doing his PhD at the University of Delaware, and my advisor, Dr. Hanning Wang from Virginia Tech. The online business has been becoming prevalent in our daily life, and one key to succeed for many online sellers is to establish a high reputation through the possible reviews from users, because the reviews can significantly impact customers' decision-making. To receive trustful reviews, sellers may invite professional reviewers to write reviews by providing free products or other extra compensation. However, because it has been widely abused, many platforms, such as Amazon, have banned such incentivized reviews. On the other hand, business may highly motivated to fabricate fake reviews to boost their reputations. One recent trend is the incentivized review group, which is a marketplace for trading the reviews. With such online groups, sellers can post the product information that need favorable reviews, and the reviewers then can claim the text from the groups, make a real purchase, and write possible reviews on the online e-business platforms, and finally submit the proof of the reviews to earn the free products or extra rewards. It can be seen as a case of crowd-turfing, but the sellers and the reviewers are organized in an ad hoc way. One benefit in such activities is that all the purchases here are real transactions, and each reviewer deals with their own orders, so it will be very difficult to be detected. In this paper, we study the incentivized review groups by collecting the data across different social network platforms to answer the following questions. First, how the incentivized review groups advertise themselves on different social network platforms, and is the incentivized review group a serious problem on the online business platforms? And finally, how can we detect such incentivized review groups? We then describe the data collection of the incentivized review groups in our study. With the text and the participants collected from the groups, we were able to collect the real spam reviews on Amazon. Probably it's the first time we can construct a spam review dataset with the ground truth. We collect data from 3 popular social networking platforms, including Facebook, Douban, and WeChat. There are many Facebook groups abused by the incentivized review groups. In Facebook, different sellers can simply post their review request to attract the participants. We select 20 most active public incentivized review groups on Facebook, and we also sign up for 2 private groups by sending the request. In total, we collected 47,000 posts and more than 6,000 sellers who post the review request on the groups. The Douban group, which can be seen as a Chinese version of Reddit, are usually used to share and exchange the incentivized review group information. We mainly collect WeChat groups from Douban because the WeChat groups are all private. Different from the Facebook, the WeChat groups are typically owned by a broker who will be responsible for posting the review request for the sellers. Since we found the tasks in many WeChat groups are duplicate, So we collected the post from the largest one and used the data for the detection evaluation in the following part. In addition, after we collect the task post in those incentivized review groups, there are some efforts required to collect the relevant products on Amazon, since in such review groups, the sellers will never post the URLs to avoid detection. Instead, they always post a short product description with the product images. To identify the correct products, we collect those pictures and utilize the camera search function provided with Amazon's app. When searching the products with images, Amazon may return a list of products, and we manually check the product images to locate the correct products. We next present our measurement analysis based on the data collected from the review groups. First, we found that many groups attract a large number of group members, including both sellers and reviewers, and quickly become very popular during our data collection. Most groups have around 5,000 group members, and the largest one has more than 40,000 members. Over months of data collection, we found 7 groups that attract more than 1,000 new members to join the groups. The sellers play a central role in the review groups for posting the review request and attract the reviewers. In our dataset, most groups have more than 1,000 sellers participated, and the largest one include more than 2,000 sellers. Also, sellers may join many review groups to reach more people and obtain more reviews. We can see that roughly 10% of sellers join more than one group, and one of the most aggressive sellers joins 9 review groups at the same time. On the other hand, the number of review requests posted in a review group indicates how active a review group is. We found many review groups are quite active during our data collection. The most active one in our dataset has roughly 2,500 review requests every single day. Sellers also send duplicate review requests for their products that are urgent for the favorable reviews to boost their sales. For example, by labeling the duplicate reviews across different groups, we identify that one of the most active sellers was performing a campaign by posting the request in one group for a short period and then switch to another one. We investigate the relationship between the sellers and the manufacturers of the products. We observe 3 different types of such relationships. First, the seller and the manufacturer may be with a one-to-one relationship, and they are clearly the same entity. Also, they may demonstrate a many-to-one or one-to-many pattern, where multiple sellers work for one manufacturer or one seller works for multiple manufacturers. In the next part, we explore some intuitive approach to model and detect the incentivized review groups. We model the reviewers as a co-review graph and refer to the problem of review group detection as the community detection problem. We then leverage the graph analysis algorithms for the community detection to identify the review groups and evaluate the effectiveness of different algorithms. In a co-review graph, Each node represents a reviewer, and each edge represents a bilateral relationship between two reviewers, where both reviewers write a review for at least one same product. To improve the detection, we integrate different features to construct multiple co-review graphs, each of them derived from one of the features. The first feature we leveraged is the frequency of co-reviews, which significantly reflects the cooperation from two reviews. To use this feature, we built the graph with reviewers having co-reviews for at least twice. The second and the third features are both fundamental time series features, which are highly associated with the intensive activities for writing reviews for certain products. Recall that we aim to build the co-review graphs for analysis. We then first construct individual graph from each feature, called FC graph, CB graph, and PN graph. We then try to compose these complementary features to improve the detection. Since the FC graph is the most fundamental one, we will gradually add the edges of the CB and FN graphs to the FC graph with weights. With the co-review graphs constructed from the features, we explore 4 basic community detection methods. The CPM constructed the communities from K-cliques, where a clique is a fully connected subgraph with K nodes. We empirically choose the 4 cliques which give us the best result. The low-end method first identify the small communities and gradually integrate the nodes with the small communities. The LPA method first assign a small group of nodes with labels and then propagate the labels within the graph. The nodes end up with the same label can be considered as in the same community. The last one is the InfoMap, which leverage random walk with probability so that it will be stayed longer in the dense part of the graph. We first studied the consistency by using those different community detection algorithms. From the measure of the AMI, the adjusted mutual information, we can see that the LPA and the low-end produce very similar results, but the InfoMap gives very different results from others, mainly because it constructs a very large community with many nodes. And then we examine the results composing multiple graphs with different community detection algorithms by varying the weights. As we can see, composing the CB graph significantly improves the accuracy of LPA, achieving the accuracy close to 80%. Composing PN graph improves low-end and the CPM method, but the accuracy remains lower than the LPA method. So here we choose the LPA for tuning the weights. With the weights of CB and FN graphs as 1.0 and 0.9, we finally achieve a detection accuracy of 85%. Let's take a look at the result of the review groups detected from the community detection method. In this figure, the size of the circle specifies the number of nodes in the community, and the y-axis indicates how many co-review edges in the communities. The most active review groups include more than 1,000 reviewers in our dataset. By taking a close look into the group, we found that the co-review relationships are highly connected among the most reviewers. In the last part, we apply our detection to a widely used dataset, which includes 140 million Amazon reviews collected from 1996 to 2014. And our method identified more than 1,000 reviewers in the co-review graph and identifies 31 review groups. The same research group also published a follow-on dataset which includes 90 million reviews from 2015 to 2018, from which we successfully identify more than 6,000 review groups and almost 200,000 reviewers in the co-review graph. In sum, we can see that since 2015, the activities in the incentivized review groups has become much popular and may cause more serious problems in the ecosystem of online platforms such as Amazon. To summarize, in this study, we collect data from incentivized review groups, which provides us a chance to construct the ground truth for the online review system. We explore a fundamental analysis based on the co-review graphs with the features, and we leverage the community detection problem to identify such activities. The detection of review groups with the ground truth data could be further used to improve the existing spam review detection framework or other AI-based mechanisms. This concludes the talk. Thank you.
Hello everyone, thank you for joining and listening to this presentation. This presentation is for the demonstration of the short paper, Perturbing Smart Contract Execution through the Underlying Runtime. I am the presenter, Pinchen Cui. Here is the outline of the presentation. We have total 24 pages of slides with 4 sections. We will start with the introduction and introduce the basic background of the blockchain runtimes. Then we will present the runtime problems we have identified in Hyperledger blockchain. And finally, we will do the discussion and conclusion. So now let us start with the problem definition. Due to the huge success of Bitcoin system, the popularity of blockchain and blockchain applications has significantly increased in the past few years. The smart contract is the main functionality enabler of blockchain applications. Most of the fancy features of blockchain applications relies on the smart contracts. In this case, the security of smart contracts also determines the security of blockchain systems. However, several attacks and flaws in the smart contract systems have been observed and reported in the past few years. One of the most infamous attacks was on a decentralized autonomous organization platform, also known as the DAO attack. This attack uses the unchecked fallback functions in the smart contracts and allows the attacker to recursively withdraw coins from the smart contracts in a single transaction. So finally, the attacker can steal the majority of the coins from the DAO platform. There are also some other attacks, but the majority of them exploit the internal programming vulnerabilities. So based on the problems found in the program level of the smart contracts, the verification and validation of the smart contract codes becomes the security criterion. However, in this project, we propose a different angle on this problem. We don't care about smart contract programming. As long as we can perturb the execution of the smart contract, all the previous verification and protection frameworks can be bypassed. This can be achieved by attacking the underlying runtime of smart contracts, that's a Ethereum virtual machine in Ethereum and a Docker container in Hyperledger. We mainly focus to investigate the potential security problems in the Hyperledger Fabric system. Now we'll introduce the smart contract runtimes. So the user of smart contracts and blockchains may use different devices with different operating systems, and they may be also different hardware architecture based. So in order to make sure all the users can generate the same output from a particular smart contract, the blockchain systems need to use virtualization to provide cross-platform capability. So generally, there are two types of implementations. The first one is container-based, and the second one is virtual machine-based. So Hyperledger uses Docker containers as its runtime, and Ethereum uses Ethereum virtual machine as its runtime. And Ethereum virtual machine, of course, is a virtual machine-based approach. So in this project, we mainly focus on the containers part. So now we introduce some more details about the container lifecycle in the Hyperledger system. So suppose we have a piece of chain code, and the chain code is the alias name of the smart contract. So we need to run a piece of chain code in the Hyperledger system. Need to go through 6 steps. The first step is packaging. The Hyperledger peer needs to package the chain code into some compressed format file. And then the second step is the installation. The compressed package is delivered to all the peers that need to run the chain code. This peer needs to build, compile, and install the chain code locally. And the third step is the definition approval. So the corresponding channel members need to vote and approve the definition of the chain code, such as the name of the chain code, version of the chain code, and the policies of the chain code, like who can execute and who can validate. And the fourth step is the commit. If the approval succeeds, then the definition of the chain code is committed and accepted by all the members in the entire channel. And the fifth step is the instantiation. So the chain code now can be initialized as an active container in the local peer. The compiled chain code binary will be added into a base image to create the real instance of the chain code container. So finally, the operations of the chain code, like the query of the chain code and the invoke of the chain code, can be carried out by the communication between the peer container and the chain code container. So what is the problem inside this lifecycle? So we have identified two problems in this life cycle. The first one is the insecure communication, and second one is the loose image management, or also we can say it's a malicious image. So first, we will introduce the insecure communication. So in order to investigate the communication, we capture the communication traffic between the peer container and the chain code container when a query transaction has been sent to the blockchain. The communication is TLS version 1.2 enabled. The encryption of the communication was based on the ECDH key exchange, and the authentication was provided by mutual certificate verification. So normally the story would just end up here and presume the communication is secure, because the ETLS is already there. However, the problem just comes from the nature of the permission blockchain and the Docker container. So Hyperledger is a permission blockchain system. The permission blockchain system requires the network to be a designated group of organizations and entities. And the enforcement of the network regulation relies on the authentication. In other words, all the entities need to have corresponding certificates and keys for authentication and verification. So all these cryptographic materials are pre-generated and stored and shared in the entire network. But for the container's perspective, the keys and the certificates need to be loaded into the container at the point the container is created, so that the containers can join the later communication. In this case, all the cryptographic materials are stored in the user space. They are accessible on both hosts and containers. So you can see from the left figure, one can access all the certificates and keys, and they are also now stored in the encrypted manner, so you can access the key with plain text. So this situation leads to a very weird problem that you can actually man the middle a smart contract. So Hyperledger uses ECDH-based key exchange, and the authentication relies on the certificates. If anyone has access to any of the containers, he can also have the access to all the certificates. Note that Hyperledger containers comes with the root access as well. That means if you have the access to the container, you can do whatever things you want inside the container. So as a sequence, the additional communication flow to the chain code container can be man-middled or attacked. So if the adversary has access to the certificates, he or she can set up the man-middle channel between the containers. By replacing the random number shared between the two sides, the adversary can use the certificates to bypass later authentication as well. By setting up this man-in-the-middle channel, the adversary can perturb the chain code invoke and chain code query. Upon modification of the invoke parameters or the execution return results, the chain code invocations will be filled during the endorsement procedure. Namely, one can deny of service a particular peer from executing smart contracts. On the other hand, the adversary can also intercept the return results of the chain code query operations. So the query of chain code data or the blockchain data can be manipulated by the adversary. And now we will introduce the second problem, the loose image management. When the chain code container is created by loading chain code binary files into the base operating system image. So one potential strategy to attack the integrity of the chain code is to poison the base image. The original Hyperledger version 2.1 base operating system image is a Linux Alpine-based image. It is super lightweight and it has a size with only 7 megabytes. So we first replace all the base operating system image to Ubuntu-based image. It has a 74 megabyte size. So in addition, we installed Python and some other libraries and modules in this Ubuntu-based image. So finally, it comes to 130 megabytes. And then we tag this new image with a corresponding base operating system name. So we observed after the image alteration, all the chain code containers has been installed with the Python additional libraries. That means the entire system has been poisoned. Why would this happen? Because there are two ways to run a container. The first one is to use the name tag. The second one is to use the hash. Although the hashes are provided by Docker, using tags are more convenient. Hyperledger Container Lifecycles uses tags to run containers. Docker can provide the integrity of all the images, but it cannot stop the user or the adversary from assigning a malicious image with a particular benign illegitimate tag name. That is also why our malicious image can be called after the alteration. So if the adversary can either redirect the user to download the malicious image or somehow modify or replace the base operating system image, the entire system can be corrupted. This malicious image can lead to denial of services, abusive use of the resources, and authorized access and information leaking. We can also use this malicious image to launch the aforementioned man-in-the-middle attacks. So Hyperledger outsources Docker as a chain code runtime. So then the security of smart contracts is bundled with the Docker security. It actually doubles the attack surface. The malicious Docker images problem has been a concern for a while. By uploading malicious images into Docker Hub, the attacker can generate $90,000 from the million downloads and deployments of these malicious images in only 10 months. So here we introduce the countermeasures of the attacks. For the malicious image part, so of course it's not practical to forbid all users from changing the tag names of all the images, but the Hyperledger system should regulate all the evocation for the containers to be bundled with hashes instead of tags. So each time the container image is called, the hash needs to compare, including all the on-the-fly generated chain code images. And the second part is the access control. So if it is not necessary, all the Hyperledger containers should be run in rootless mode. This can limit the adversary from performing some harmful operations like access the private keys in the containers. And for the communication security part, actually it's a twofold problem. The first part is the confidential cryptographic materials loaded into the containers. And the second part is the use of the additional communication between the peer container and the chain code container. The key materials and the certificate materials loaded into containers is a side effect of the malicious image and loose access control. If you can fix the malicious image problem and the loose access control problem, actually the first part is not exist at all. But for the additional communication part is slightly different because it's additional communication that does not exist in some other virtual machine-based runtimes. So can we really get rid of this network communication? So note that the communication between any peer and others may be remote network communications, but for the local system data exchange between the chain code container and the peer container, the network-based communication is not the only option. So Docker supports the shared memory for inter-container data exchange. It is based on the inter-process communication namespace. So instead of using network communication, using IPC to transfer the chain code operations will be better and more secure. So now we come to the discussion. We'll discuss whether this attack can be applied on Ethereum or other blockchain platforms. So generally, it may seem that Ethereum is more secure because its runtime EVM is a customized in-memory stack machine. But actually, EVM stack overflow attack and another CVE 2018 attack perturb the normal execution of a smart contract based on the runtime level flows. Although these two flows has been already fixed, the concept of runtime level attack on the virtual machine-based runtime is already proved. So there are some other blockchain and smart contract platforms like EAI and NEO, but they are all virtual machine-based. So the threats and concerns for all the other RAM-like runtimes will be very similar. So now we have a new threat model for the smart contract system. So we need to care about both the programming level security and also the runtime level security. We need to care about the image security, access control, community security for the container part. But for the virtual machine part, we need to also care about something else because unlike the container implementation, you have a uniform runtime that is Docker container. For the Ethereum and virtual machine part, you may have a diversified implementations. You may have a different implementation of the virtual machines, like in Python, in C++, and some other third party also provide their own implementation of the virtual machines. So you need to keep track of all the security of all these implementation, this may raise some other additional security concerns. So the conclusion and contribution of this project. So we propose a new attack vector on the smart contract ecosystem. So instead of focusing on the smart contract programming level, we propose to perturb the smart contract execution at the runtime level. And then we perform a detailed case study on the Hyperledger Fabric system and to prove the feasibility of the proposed attack. And the third is we summarize and demonstrate the countermeasures of the proposed attack. And finally, we propose a new threat model for the smart contract system. And here is the references used in this presentation. That's all for this presentation. Thank you for listening.
Alrighty, hello everybody. I'm Kevin Butler, one of the TPC co-chairs, along with Nitesh Saxena. We have been overseeing the technical program, and it's my privilege to bring the SecureComm conference to a close for this year. Nitesh gave the opening remarks, and I'm going to give some closing remarks. And before getting into those, I wanted to discuss the best paper. SecureComm has a long tradition of providing a best paper award. And I want to tell you a little bit about the process that we used in order to generate the best paper and what the final result was. So the best paper award process had to do with nominations being received for the best paper awards. We, based on the nominations, created a short list and then a list of finalists from there. And then there was a vote by the technical program committee on the winning paper. So we had a number of really excellent submissions this year, and we're very happy with the program, and I hope that you've been as well as you've watched over the last few days. But a few papers really caught the imagination of the TPC, and let me tell you about what those finalists were. These were the two finalist runner-ups for the Best Paper Award, both great papers. The first one is Coronavirus Contact Tracing App Privacy. What data is shared by the Singapore OpenTrace app? It's from Douglas Leith and Stephen Farrell at Trinity College in Dublin. It's one of our finalists. And the other was Smart Switch, Efficient Traffic Obfuscation Against Stream Fingerprinting from Haipeng Li at the University of Cincinnati, Ben Yu from the Chinese Academy of Science, and Boyan Wang from the University of Cincinnati. So great papers, and congratulations to both of your papers for being amongst the final shortlist. Now, the Best Paper Award for SecureComm 2020 goes to the following paper: Transnet, Unseen Malware Variance Detection Using Deep Transfer Learning by Candon Rong, Gaopeng Gu, Mingjin Kui, Gangzhong Zhenli, and Li Guo from the Chinese Academy of Science, the Institute of Information Engineering, and the School of Cybersecurity at the University of Chinese Academy of Science. So congratulations to the authors. Unfortunately, because this is a virtual event, we would love to present you the Best Paper Award in person, but you will have to we'll have to do this remotely, and please accept our congratulations. And again, to all of the papers this year, they were great papers, and we've been very happy with the program that we put together, and our Best Paper Award candidates were all uniformly excellent. Now, it's my honor to bring the conference to a close, and I'm going to close by looking forward. So next year, hopefully we'll be able to do this in person if everything goes well. And already looking forward to SecureComm 2021. The conference will be held in Canterbury in the United Kingdom. And we have the two general chairs for the event. The general chair for next year's SecureComm conference will be Shenzhen Li, who's at the University of Kent. And the general co-chair will be Radha Puvendran at the University of Washington. So let me close now by saying thank you to everybody who was involved in making this year's conference a success. I know that it was this is a uniquely challenging year for everybody, and everybody from organizers down to authors to attendees. This has been a major sea change in how we do things. Perhaps we can learn some lessons from this year that move forward in terms of how we consider talking together as a community in the future, but we really are grateful to all of you who've been flexible and adapting to this new landscape. So we thank all of the authors who submitted papers. There was a great batch that we looked through. We thank the presenters for the great talks. We thank the technical program committee for their substantial work in putting this program together and going through multiple deadlines and looking at multiple rounds of papers under significant time pressure. They did a fantastic job. Over 600 comments been written, over 250 reviews in total. So please take a moment to acknowledge the tremendous contributions of our technical program committee. And then thanks to you as attendees for participating, for the Q&A that you've offered during the conference. And again, by keeping the community going and sustaining sustaining SecureComm and the security community in general through these uncertain times. And thanks to EAI for all of their work organizing and seeing their sponsoring SecureComm. So with that, I'm happy to announce the end of this year's SecureComm 2020, and I very much hope that we will be seeing you, hopefully in person if all goes well, next year. Thanks again for a terrific conference.